Good afternoon, everyone. So we go ahead with the third talk on the radionuclide technology, and this is by our colleague Daisy. The topic is on statistical analysis to advance our common understanding on sauna false positives hypothesis.
Good afternoon, everyone. My name is Daisy, and I'm going to take on this topic on the sauna false positive hypothesis. So I'll start with the background of the CTBTO and talking about the radionuclide stations. So the CTBTO has about 80 radionuclide stations all over the world, in which 40 will be equipped with the relevant isotopes, that is the xenon-131M, xenon-133, and xenon-135M. So in the CTBTO, there's the IDC Center, which operates a dedicated analysis software for processing spectral data from the IMS data systems. So the analysis of the beta-gamma coincidence noble gas data is based on a net count calculation method, which in its standard implementation only performs interference correction if a positive net signal is present. And this is the standard method, and what you see here is what it does. Based on the flowchart here, you can see the subtraction is done when the count is below, when the counts are above the LC. And for the new configuration method, there's no subtraction of the xenon isotopes. So what it does, it systematically subtracts the radons from the system without checking it first, compared to the standard method. So for the analysis, based on previous studies, it was reported that some of the detections seemed to show an overestimated rate of false positive for some of the isotopes. So we wanted to improve the analysis results, and based on the new configuration method, which systematically performs the interference correction, we tested the data in offline mode, and we statistically compared the results with the standard NCC method. These are the stations that we focused on, and the data was approximately of 2,500 samples over 3 years, from the year 2014 to 2016, for 7 sauna systems. And the stations were in Rio de Janeiro, Santiago, Japan, New Zealand, Sweden, and Charlottesville in USA, and the other one in Chile. So the statistical tests were performed on the non-detections of each isotope and each sauna detector system of considered sauna systems, which gave us about 84 data visualizations from each system. And we compared the results between the two systems to see which system had a better performance. And the results we tested, we checked the normality test based on the skewness, the kurtosis, and visualized through QQ plots and probability density graphs. But what we discovered for the xenon-133, the detection rates were the same in both methods. And for the other, so our work focused on the isotopes xenon-131M, 133M, and xenon-135. And the next slides will illustrate our results. So the first bar graph gives us the overview of the findings, which is the percentage of the detection rates from the two methods. This one, the graph on the left, yeah, it shows the standard method and the percentage of false positives on the standard method. And the second graph on the right, the second part of the bar chart shows the new method, which indicates a low percentage of the false positives, which is 19.03%. So for the first isotope is xenon 131M for the BRX 11004 station. And the bar chart shows the percentage of false positive. If you look at the second bar chart here, you can see that the new method indicates a low false positive rate compared to the standard method, which is the other one, the 10%. And also that is illustrated on the probability density graphs shown there, and the QQ plots, which were meant to show us how our data is distributed in the data set. So if you look at the way the data is distributed on the first side, on the left side, this side, here, that is the standard method. And if you look at the probability density graph compared to the second one, where it's written UNCC, you can see an improvement on how the data falls into the normal distribution line. And for the QQ plot, you can be able to see that the quantiles also fall in a straight line on the new method, meaning that there's an improvement after the tweak in the system was done for the xenon 131M. If you look at the results for the xenon 133M, they're also comparable, and the analysis results also show a better performance of the second method compared to the first one. The data from the QQ plot lies on a straight line. It fits a little bit better. And also the probability density function graph and the Poisson distribution seems to be more in line into the normal, falls into a normal distribution, and the mean and the median are almost zero, which is a good sign. So in summary, the frequency distribution and the QQ plots were used to test and illustrate the normality hypothesis of the standard NCC method and the new configuration method. And based on the results that you've seen, the new method seems to show better results statistically compared to the standard method. So, and our results were focusing on the xenon 131M, the 133M, the 135 only. Yeah. Thank you.
Thank you, Daisy. I think we do have time for questions. Yeah, please, Ted.
Thank you for your presentation. It's a really great topic and good to see a new face working on these issues. I have some concern about using station data for this analysis. Mm-hmm. Station data will be contaminated with the actual isotopes that we're trying to determine whether they're there or not. And while that should be part of the analysis, using it by itself without an augmentation, say by a simulation or maybe a detector in a controlled environment when you know what isotopes are there and what isotopes aren't there, would augment your study and probably strengthen your conclusions. I'll say that I do agree that removing the binary decision is the right thing to do. I've been saying that for quite a while, and that just, I think, sort of logical. But I really think that something needs to be augmented and not just use station data that may or may not have the isotopes, and there's no a priori way to know that. Thanks.
Hakib, do you want to comment on that?
Yeah, thank you, Ted. Indeed, this is actually a good point before moving ahead with this, with the dropping the binary decision. I think as the next round, we will have to look at Monte Carlo simulation and some cross-check whether this is what we will get in terms of false positive rates, simulating samples with zero activity.
Yes. Yeah, that's what we need to do, and that has been done.
Yeah.
In one of the, I have a poster on that with also with a new method that shows the same result as you have also. So it works like that. So,
Yeah.
but I think you should call this detection rate instead of false detection rate.
Yeah.
Then you are.
Yeah.
That's what it is actually. So, but the results are fine, I think.
Yeah. Then now maybe in terms of status of the software modification, the change is already right now being deployed in IDC operation, but the question is whether we still need to wait for changing this to the new configuration, or that some more discussions are needed, maybe, I don't know. So otherwise, the software, technically speaking, is ready in the IDC operations.
Can I? Well, I think we agree here that I don't think we need to wait anymore for that.
Good, perfect. And we have at least 100 people here. Good, thank you. Okay, then is there any other question to Daisy? Otherwise, the second presentation is by me. So this is now about software development for processing the data from the next generation systems, but also from the currently operated systems. Which means that's why we use the word unified. Unifying, which means fighting against software proliferation. So we'll start with a short introduction, then we will highlight what is specific for each noble gas systems, I mean the new, but also the current technology, and then what is also similar in terms of analysis algorithms. Then we will also step back to the physics, and then talk a bit about the regions of interest and the specific needs for each system. Then autostrada, in Italian this means highway, but this is also the acronym of automatic software tool for radionuclide data analysis. So it's autostrada. Then we will summarize. Then how to... Okay, so currently we are operating both high purity germanium, but also beta gamma coincidence. Out of the 25 systems in IDC operations, 15 are sauna, and the sauna is using sodium iodide for gamma coupled with the plastic scintillation detectors. Then there is this silicon pin-based detectors for beta, which improves the energy resolution, which helps also discriminating the two metastable isotopes of xenon. In terms of status, actually, two of the next generation systems are already under acceptance testing. It's 1 year of performance assessment, and it comes to Sauna 3, which went through 6 months of testing in Stockholm, and a couple of weeks ago it started sending data from Charlottesville in the US within the second half of the acceptance testing. The second system is the Spalax NG, and here NG not in the sense of noble gas, but rather next generation or new generation almost. The system went also through 6 months of testing in Paris, and now it is in the process of being moved to Canada for 6 more months of testing. Other than that, we also have Xenon International, which is a US technology, and MIX, which is Russian Federation, which are almost ready to start the one-year acceptance testing. Each system has specific design features because the main goal is to improve on top of the current operational systems. And that's something that we need to take into account in software development. The CTBTO needs to be prepared. We have to make sure that before deploying the very first next generation system at IMS stations, we will have the required software to process data in automatic mode. When we started with the Spalax NG, there was no software. And that's why we initiated this project. This is now basically the physics in terms of decay scheme for Xenon 133. We have the gamma at 81 keV, and we have the X-rays, and here is the beta continuum, and we are using the beta-gamma coincidence region of interest for quantifying the Xenon 133. Xenon 135 is also the same. We use beta combined with the gamma, apart from the energies are different. Otherwise, we also have a similar ROI at a different energy. Metastables are quite different in the sense that the decay is not happening by beta decay, but rather through conversion electrons, and that's why we have this Gaussian shape for the Xenon 131M at 181, 29 keV. And then we get this like ellipse as a region of interest for quantifying this isotope. The situation is similar for Xenon 133M. It is also, it has a conversion electron at a different energy. Otherwise, it is sharing X-rays with the Xenon 133M, and then that's what allows us to quantify this isotope. Now, if we combine the four isotopes together, we get something similar to here. So we have one region of interest for each of the four xenon isotopes, but that's not enough. Taking into account that in theory, the gas processing is supposed to ensure very high purification of radon, but that's not the case. And that's why we also need one more region for lead-214, and this is a decay product from radon. And then that's okay for sauna, for mix, but also for Xenon International. But Spalax NG is also using one more region of interest, and this is what we call ROI 0. And this is for taking into account interference contribution from bismuth-214 to the lower energies. Now, if we compare the different technologies side to side, in terms of key regions of interest, we have everything is the same apart from bismuth-214, which is only used by Spalax NG. Then, the histogram block. Sauna is using 256 channels in gamma and beta, and that's enough to use just ASCII format, which means we have the normal numbers in the channels. Spalax NG, because it is using high resolution beta and high resolution gamma, then the channel size, the matrix is quite much bigger, 10, 25 times 40, 96 channels. If we keep using the current way of reporting the format, then we end up with 8 megabytes, very roughly, for each spectrum. And that's why there was this solution which was nicely and efficiently implemented, and which consists of encoding and compressing the histogram block. So the rest of the PhD, the sample spectrum file, is the same, but only the histogram block is compressed. I mean, encoded base 64 and compressed. Then it's also something that needs to be taken into account in the software development. Now, interference ratios, we have quite a lot of differences. For instance, bismuth 214 is only used in Spalax NG. Xenon 135 is used in both Xenon International, this is the name of the US technology, and Spalax NG. Xenon 133M is only, at least currently, we have the interference factors only in Spalax NG. So it's yes and no. Correction for memory effect is not needed for Spalax NG, and this is something that we take into account in the other technologies because of the counting cell is in the plastic scintillator itself. Then Xenon 131M and 133M, we are using K-alpha plus K-beta, which means we are combining X-rays for sodium iodide, because that's the resolution. But for Spalax NG, thanks to high purity germanium resolution, then we can see the fine structure. And here we only use the K-alpha for gating the metastable isotopes. Now, in terms of net count calculation method, the flow chart is the same. The physics is the same. We have specificities among the technologies, but the overall flow chart is the same. And we only need to put a bit more intelligence in the algorithms to make the same software understanding data from any system. That's what we did through this software, as currently we have no tool at the IDC that handles Spalax NG data, for instance. It's not available. Then we started this development actually in late 2018, in October, and now the project is Autostrada, which uses open source, license-free, modern development framework, and it shares the same library with Inspire, which is the integrated platform for the interactive analysis. And the same software will be delivered to both IDC operations, but also integrated in the NDC box software. I have to check my watch. Good. So the software handles both low resolution and high resolution, and there is no need to tell anything. I mean, to tell the software that this is Spalax NG high resolution, or this is Xenon International, you have more interference factors, or different otherwise, or this is sauna or mix. So all this is automatically done by the software. The software is written in Python. It is intended to generate automatic results for interactive review using Inspire platform, which means we are working on both for the integration under the standard environment for both IDC operations and NDC box, but including database schema and so on. But on top of that, Autostrada also offers the option of standalone mode. You don't need any database. You don't need, it has an integrated parser, and it runs just in completely standalone mode. By the way, it runs also on Windows because it's Python, it's cross-platform. This is what we tested. So it works on both. It also generates the output in integrated mode. The output is stored in the database. In offline mode, it produces analysis reports with the results, including some graphics on the regions of interest. Then it also has the option to be running with the graphics so that you can interact with the spectra, both in coincidence but also the gamma and the beta spectra. Now, so DGS stands for detector, gas, and sample. This is the data components that Autostrada supports as input, depending on the case. So it has a small routine. It's actually 5 to 6 lines for unzipping and decoding the histogram from SPALAX data. And then detector background subtraction is performed for all systems. Gas background is skipped for SPALAX MG. Interference factors is done for whatever factor is available in the interference block. So it handles this in a fully automated mode. Now, we talked about the input data. The output is the standard NCC results. In terms of, for each xenon isotope, we have an answer whether the isotope is detected or not. This is comparing to LC. LC is calculated at 3 levels. First of all, in terms of for the net count, then in terms of activity at acquisition start, then also in terms of activity concentration. And the decision is actually made just at the level of the counts. Then all this comes with the required, associated uncertainties. Now, this is a comparison for one analysis. By the way, here you see, actually, we almost got surprised when we saw the very first spectrum from SPALAX NG, because we were not used to this fine structure, where here we have just the K alpha, and there's 2 smaller distributions are also from xenon 131M, which means if we gate using K alpha, we get these ROIs. Then if we gate using K beta, then we get the counts here. And the same, the brightest distribution here is K alpha for xenon 133, and K beta for xenon 133 is also here. And then the bar plots here show the Autostrada results compared to the French software. And it's not by chance, and this is not the only case where we had almost 100% consistency, which is also a good way of doing benchmarking, which means we develop the software using the same algorithms, but in a completely independent way, and this helps and optimizes the software validation related work. Then that's all. Tomorrow afternoon, for those of you, and we saw that the list is really long, for the tomorrow's side meeting on Noble Gas in the afternoon at the VIC, we will spend some time for a live demo on this software as well. Thank you.
Hakeem, thank you very much for that informative and interesting discussion on the way forward. Are there any questions? Oh, there's already a couple.
So thank you for the presentation. When Autostrada will be operational at IDC, because it's a development phase, when do you plan to put it in the IDC?
Yeah, we are now in the process of integrating. I mean, it works already from the command line, and that's what we will see tomorrow. Friday, not tomorrow. And then by September, it will be fully integrated in the IDC testbed, so that the first spectra from SPALAX NG that will come from Canada will be processed using Autostrada. And then we will integrate this software in the NDC box just in a couple of months, I would say by January or so. Yeah. Thank you, Sylvain.
Justin, I believe you had a question back there. Perfect.
Like to see the progress here. It's great. Will this code be available in its uncompiled form for people to I don't want to say play around with, but that's exactly what I intended doing with it.
Yes, thanks, Justin. Actually, the source code doesn't exceed 1,500 lines. It's also optimized. This is Python, which means it's even smaller than the input data files. And this is available to anyone. Yeah.
We have time for one more question. I think we had one right here.
Thank you, Hakim. I just wanted to inform them that the SONA 3 data will not be analyzed with the NCC method in the future.
Yeah.
So for SONA 3 data, you would have to replace that with a new method that we have developed. So I guess you have prepared for that.
Yeah, exactly. That's actually part of. I mean, when we initiated the Inspire project, then with this Autostrada, we started building a common library which will be shared by any tools. And the software is now made much more modular compared to what we have in operations. And this is a new method. They didn't cover the time resolution, which is actually one of the significant achievements of this next generation systems, is that SONA 3, for instance, is running 6 hours cycle. Spalax NG is running 8 hours, but it also has a shorter processing time, which makes it 10 hours before reaching the sample and starting the acquisition. So indeed, that's another module that we will also implement, maybe in parallel just to see, but again, we will try to make this, the new method also work for the other systems. Yeah. Thank you, Anders.
I think Hakim mentioned there'll be plenty of opportunity for discussion and questions tomorrow during the workshop. Let's give him another round of applause. Now we'll move forward with machine learning to categorize radionuclide spectra.
Good afternoon. This quick talk of mine outlines experiments that I have been doing with artificial neural networks, NNs, which I have applied to radionuclide spectra review. The goal of this is to produce tools to assist the radionuclide analysts, support them in their work, but not to replace them. This and similar work that my colleagues are doing now is made possible with some equipment that we got in December. So this started around Christmas last year in my case. This particular box we have is a suitcase-sized workstation with some GPUs in it, 4 GPUs, and it's actually been very pleasant to work with, very, very efficient. In my talk, I will be oversimplifying a lot, and please don't beat me up for it. And please know that I'm coming to this as a neural network nerd, not a radionuclide scientist. The problem statement which I imposed on myself is to classify radionuclide particulate spectra into categories 0 to 5 as a human analyst would from raw spectra alone. Now, the problem of the raw spectra, a neural network needs uniformity of size. Got to turn on my watch here. All input sequences or all training samples have to be of the same length. And therefore, I picked from the database we have all the spectra that we have of 8,192 channels. We also have a handful of, or a good number of 16K and so on, but I didn't want to deal with the problems of downsampling them, or not yet. So this, of course, downsampling would bring some loss of resolution and so on. Now, of course, there is a problem with detectors around the world. They vary as well, as you well know, and better than I. Not only do they not all have the same energy spans, they begin and end at different energy levels, and so some serious tuning might have to be done. But still, with the just picking the 8,192 channel spectra, we have well over 250,000 relatively high quality human-reviewed samples that can be used for this kind of studies. This is basically the classification that we use. The categories or levels on the left here, 1 through 5 is the same as we use, human analysts use. The category 0 is just a convenience for me, anything that was released without category. This was meant to be for my convenience, but it turns out to be inconvenient, in fact. The problems, if you look at this, are inherent. Problems inherent in this are quite clear. Built into this classification is what it means to be normal. Spectra recorded at one location or at one time might be perfectly normal there at that time, but in a different location or a different time might be abnormal. So this may make sense to a human analyst, but it's difficult for a neural network that's trying to determine or classify what spectra is abnormal and so on. The history and location of the detector the need for this may make it impossible to cleanly separate the spectra into classes. So this is what we know starting up, and even because I'm coming at this from a radionuclide ignorance, I might theorize, okay, what's the most important thing I want to learn here from the sample? Is it the shape of the peaks, which are relatively easily recognized and learned by using convolutional neural networks, CNNs? Or is the primary importance the location of it? And of course, you can tell me, peak at the left end of the spectrum is not the same as the right end, which is different from what we are doing in normal image processing with convolutional neural networks. You might be recognizing cats, for instance. A cat image, I mean, a cat is a cat, even if you turn them upside down, but a peak on the left is not the same as a peak on the right, obviously. Now, neural networks are sometimes seen as black boxes, and if I do nothing else in my talk today to convince you that this is quite easy to work with, I would be happy. The neural network is a mechanism to produce a mathematical function that separates multidimensional space into well-defined subspaces or mappings onto categories like I am doing. And similar to what we are doing when you have a set of points in the two-dimensional coordinate and you're trying to fit a line through it, we are subject here to overfitting and underfitting exactly similarly. But once we have this, if we manage to take the training data set, nearly 250,000 samples, say, and cleanly separate them into well-defined subspaces that correspond to the categories, then I can take a random unseen sample, throw it into the same function, and it ends up in some part of the space, and there I have my classification. That's the theory, at least. Now, the neural network takes the spectra, applies the function to it, and comes out with a category. This, of course, we have a huge number of spectra, and each spectra is large in terms of storage, 8,000 floating point numbers of some sort. But in theory, this is just linear algebra, and there is nothing really groundbreaking here. It's something that Gauss couldn't have been working on back in the 1850s or earlier even. But now we have the power to actually calculate these things without going nuts. Now, a neural network, what does it do? It takes in spectra, calculates its function value with some random values in it for its function, comes out with a wildly incorrect estimate, and when we compare it against what the human analyst came up with, calculates the difference between the true human value or human assigned value and what it calculated, and somehow distributes the error back into the matrices that implement the function. Then we try again, hopefully getting a bit closer, back propagate the error, try again, and continue like this until we get closer and closer to the value that the human assigned. And that's all there is to it. Lots of calculations, but nothing really groundbreaking here. Happily, one doesn't really need to know these details about a neural network to make use of them. Many open source toolkits are available, fantastically powerful packages that are available for free that essentially remove this. Of course, understanding is nice, but you do not need to bother with the details of the neural networks. The programming is done. You can just focus on the physical problems or what you find out. I have, in this, when I started doing this around Christmas, I have been using TensorFlow, which Google originally distributed, Keras, another package to make this easier to use, running on Python in Jupyter notebooks. And these are things that anyone can get for free and work with. I've used a handful of other packages, NumPy, SciPy, Pandas, mostly to deal with the drudgery of getting the data in and out and converting it from one format to the other. But I want to emphasize that this is easy to work with. Now the diagram on the right here. Okay. The blue line, just to decorate the slide, otherwise it would be boring, but the blue line tracks the progress of the training set up to about 80% and the yellow or orange line is tracking the learned network's progress on validation, a set of validation data that we used exactly to keep track of the training progress. Now here is a model I built, a black box model. Let's see if we can. Yep. I have built about, I would guess, about 50 different models to work with these radionuclide samples, because I really didn't know when I started, to an extent still don't know, which model types would be best. This particular one shows you 3 sets of convolutional layers, or three convolutional layers with different sized filters. And for those of you who are doing signal processing or have done, you will immediately know what I talk about when I say filters. These are just digital filters of length 7, 17, and 33. And there are 32 filters in each layer. And here the crazy thing is that the network learns the values of the filter. They are not predefined by me. It's amazing that it works, but there it goes. Each of the convolutional layers have a summation layer, the max pooling there, and then there is a flatten layer which brings everything down to 1 dimension, 2 completely dense layers with 1,000 nodes each, and the output 5 nodes, sorry. This is, at least to me, a trial and error process. I don't know of any mechanism to say, okay, here is a problem of certain type, what is the best model for it? Although it turns out, if you find a well-working model somewhere, even for a completely different type of problem, you can, for most purposes, grab it from the internet and use it for your own processing. This particular network had nearly 18 million parameters to train, and I think each training run of 250,000 training samples, 50 times through the loop, was about 40 minutes on this nice machine we have there, the space heater. These were my results at the time. You have category on the left, of course, cheap plotting, and I didn't do a good job of it, but you have the categories from 1 through 5 on each side. The left one is my predictions on an unseen test set. And the diagram on the right is the actual categories of the test data. So what you do is, in practice, you have, say, 250,000 training data set, 10,000 for validation, the orange line that you saw there, which is used in each training step to say how far did we get, how good are we. And then I keep about 10,000 spectra to myself until the training is done, and then I throw it at it, data that the network hasn't seen, and say, okay, how are you going to perform on this now? Now you're predicting something. The confusion matrix is somewhat confusing to describe, but most activity is there 1, 1, where my predicted value is 1 and the actual value is 1. Now, there are situations, as I mentioned up front, that make it difficult to classify things properly. And so Dr. Martin Kalinowski came up with the idea that we would be using only 2 classes, category 1, which is everything is normal and fine, and category 0, which is everything else, and let the human analysts take a look at that. Here is another fine model that I built with 38 million trainable parameters. Again, took about 40 minutes and to train. And again, I'm close. If you look at just this distribution of values, accuracy on the test data was almost 83%. But we should not forget that a constant box like this that always outputs 1 would be around 80% correct. So just the percentage here is not by itself useful. Unfortunately, I didn't save the confusion matrix from the previous one. Now, it wouldn't be complete if I didn't suggest some path forward. One obvious thing is to apply calibration to the spectra before I try to learn something from them so that they are actually comparable, the energy span and so forth. We could also apply the detector ID to the spectra, to include the detector ID as one of the trainable parameters. I haven't done that yet because I was worried about the clever Hans effect, which you may know. The clever Hans was a German horse that learned apparently to calculate, to add numbers. But it turns out that it didn't really learn anything. It was reading the owner's mimes or the face of the owner. But this is now used in machine learning terms, community to indicate that, okay, the network learned something, but for the wrong reason. So it might, for instance, focus on the detector ID and say, okay, it must be level 5, where not looking at the spectral content. This is something I don't know how to deal with yet. Now, I've just started to scratch the surface with 2-dimensional beta-gamma spectra. I haven't really done anything there yet to tell you about. Tomorrow at 11:30, just outside here, I will have the software running or some sample spectra if you want to take a look at it and ask any, discuss any questions you might have. Thank you. That's it.
Thank you, Trygve. We have the first question from Ted, please.
Thank you for your, is this on? Okay. Thank you for your presentation. It's really great to see new techniques being applied to our existing problems. In my opinion, you really need to pick the right problem to apply a neural network to.
Yep.
And it may not be the categorization. I'll give you an example. If you knew the gain of the spectrum exactly in some of your assumptions at the beginning, and you said you had an asterisk, and you said that's not true. If you knew those, you could provide mathematically an exact solution in far fewer steps, an exact solution. Okay. So I'm not sure how a neural net can do better than an exact solution ever, because you're just adding the number of counts and dividing it by an efficiency, you get an activity. If you knew that. And so the problem we're really dealing with, one of the problems is the detector response is not perfect. So I would posit that maybe neural networks could be used in that way to determine something about the response of the detector. So it's inverting kind of your assumptions, maybe using it to do some aspect of that, or maybe even to determine whether something is a peak or not, which is another problem we have. And there would be a lot of statistics you could apply to that problem, and it is an operator-intensive thing. Is that a peak? Is that not a peak? But anyway, just picking the right problem, I think, is really important here. But I do love the idea of application of neural networks to some aspect of this. Thanks.
I don't expect you want me to say anything to this, except I agree, actually, it would be. No,
Good. Maybe a second and last question, because otherwise, I think we go ahead with the waveform-related talks.
It's time to shift gears a little bit to the waveform-related talks. And first person up absolutely needs no introduction, but Bob, come right. This topic is semantic method for Kepstrel depth estimates for sequence at shallow events.
Thank you. I'm sorry to say this, but you've heard 3 talks about radionuclide, and I've worked on all the data except radionuclide. So what I'm going to be talking about, we've done on seismic, hydroacoustic, and infrasound. I've also done it on machine diagnostics, biomedical data, but not radionuclide. So with that, I'll get started. If I can, here's the thing. And my talk is on automating or semi-automating or really automating the Kepstrel technique. And I seem to be working in the area of 50s. Last year was 50th Working Group B that I was honored at. In a couple weeks, I'm going to the 50th anniversary of, I got the tie on, Apollo 11, worked on that. And I started Kepstrom 50 years ago this year. So it's a matter of 50s, I guess. So with that, I'll get going because the time is short and I have to cover a lot of material. Oops. Did I hit the wrong one? Do I? Oh, this one? Yes. Oh, okay. Okay, what we're looking at is when an event occurs underground, and we're looking primarily at nuclear events, shallow earthquakes and whatever, we're worried about what the yield of that event. First question is, or one of the first questions is, where's it located and what's the yield? And as we've learned the hard way, if the event is overburied and you use a standard depth of burial or so for the depth, then you're going to underestimate the yield. So it's become very apparent to estimate the depth of the event, be it whatever. And so because it was very intensive, and I'll be calling it a wizard code here in a few minutes, that we were tasked to automate this. And we're well along the path to automating this procedure. We need metrics, we need statistics, and that's what we're working on, and that's what I'm going to be presented. I'm going to have to cover this at a high level, so we have my cohorts are sitting over here, 2 of them, and they're going to be talking about posters later in the day. One of them is Mel Kepstrom. I'll be there. If you have questions that you want to ask, please come to that poster and ask me, and I'll try to answer it. Okay, so we're trying to automate this, and we're trying to come up with the statistics. Okay, if you go back to Bogart, Healy, and Tukey back in 1963, they talked about the power Kepstrom. It was called the Kepstrom. I termed it the power Kepstrom. And shortly there, a few years later, Oppenheim talked about holomorphic systems at MIT, and one of his students was Ron Schaefer, and Schaefer talked about the complex Kepstrom and put that into his thesis. And then they published a book, Oppenheim and Schaefer, that I used when I taught graduate school. So what we're doing is we're going to work up these metrics, and we're going to come up with a product of the metrics and the weights and see if we can duplicate what I have done in the wizard code and do it better. Simple-minded cartoon. You have an event, you get the P phase coming off to the sensor, you get the signal going to the surface, which is a little p, big P, and then it follows the P. And if you can work that time difference and you know the velocity, and I want to stress this, I'm dealing with time. Somebody's got to tell me the velocity in the source region. Somebody's got to tell me the location, because I'm not getting that. I just deal with time. So once I get time, then somebody tells me what the velocity is, then I can get the depth. So make sure you know that. So here's a simple cartoon. The bottom on the right is what we start with, and then we want to deconvolve, take out the little p, big P, and get an estimate of the P phase, and then by that, you have a better signal to maybe estimate the yield, and also you know the depth. Simple mathematical equation. This is a barrage function on the top, on the left. You don't need Kepstrom to see that there's a signal a little bit smaller to the right, and you can measure the time, so you don't need that for that. But if you look at the right, which is the power Kepstrom, well, both Kepstroms are there. The red's the complex and the blue is the power. You see that you get peaks at multiples of the depth, the time. And now if you go to the bottom one, where it's more realistic about what we're talking about, where you have a very shallow event, now it looks just like the first signal that we're saying is a P phase, and there's no way you can tell by looking at it what the depth is. But if you go over to the right and look at the Kepstroms of it, then you see that you get the peaks very similar, but shorter in time as you did above. One thing I want to point out, this mathematical expression is minimum phase, and so a minimum phase sequence gives you very nice Kepstrom power and complex, and they overvary nicely. In seismology, I don't see minimum phase sequences. They're non-minimum phase. They're not max phase, but they're non-minimum phase. If you want to know more about that, I can explain that at the poster this afternoon. Okay. I'm not quite sure what I'm doing wrong here. Okay. This is the same signal, the barrage function, with some noise added. And the only reason I put this noise and put this figure in is we have the same delays on the two models. You can see what it does to your Kepstroms. It really botches them up, if you will. And you get noise, signal to noise, poor signal noise, you get harder to look at. And this is more typical of what you deal with when you deal with real seismic data. Okay, this will just summarize those two. What I want to point out on the left is you see the modulation, the third one down is the modulation in the power spectrum, and we take those peaks out of the Kepstrom in the bottom. That's what those big arrows are about. And the top on the right is a deconvolved waveform, and I'll show you a diagram in a second on what that means. The one and the second one down, the red is original signal, superimposed on the deconvolved signal. Then you take the deconvolved one from the original, and you should get an estimate of the little p, big P, which is the next one. You probably can't see the size that are over on the left. And then on the bottom is a correlation where we correlate the original signal with a deconvolved signal with a different signal and see how well they correlate. And if it's a little p, big P, it should be out of phase, should be a negative correlation. The stuff on the right is the same thing, only it's there to show you when you put noise in, you don't see these nice modulations, and it makes things more difficult. This is the diagram I talked about. The top is the power Kepstrom. If you're dealing with hydroacoustic data and you want to know the bubble pulse or the depth of the water column or the depth of the event, you just need the power Kepstrom. You got plenty of bandwidth. It works beautifully, and I've done that for years. The only thing I would correct on the right is where it says absolute value squared. You don't want to square it. I want to know the polarity, so you don't want to square it. If you unwrap the phase, handle the phase along with the spectrum, and go to the complex spectrum domain, do a linear filtering, and like I showed you a minute ago, taking out those peaks. Then you invert the process, go back to the time domain, then you get an estimate of whatever is left after you took it out. In this case, we're taking out the little p, big P, hopefully, and we're left with a P phase. Okay, this just summarizes what I just said, so I'm going to go on. I have to hurry here. And I'm going to show you a textbook case. This is not seismic data. This is infrasound, but it's really shockwave data from the experiment about 2011 in Israel. And a bunch of exposures, it was on the surface, it was set off, and there were some infrasound sensors a few kilometers away. And this is like textbook to me, that's why we put it in here. The top is just another way of doing that diagram that I just showed. I'm talking about metrics. I'm going to have to go quickly on these metrics, but I'll show you in data what we're really talking about in metrics. But at the top, these data were sampled at 1,000 samples a second. So that's why the modulation in the top one is quite good because in high frequency because it's 1,000 samples a second. And then the next one down is the unwrap phase, and the third one is the unwrap phase with the linear trend removed. And you can't see it in this picture, but in the next picture, not the next one, but the one after this. And there's the Kepstrom for this, and you can see for this real data, shockwave data, you get very nice power and complex Kepstroms. But because the two signals are in phase, which is not typical of a depth phase, they alternate. The first one's positive, the second one's negative, the third one's positive, so forth and so on. Where if you have a depth phase, they're all negative. Okay, here's some more metrics that we'll put off to, if you want to see more about this, my team can explain these more. But I'll kind of explain them in a little bit. Okay, and more. So to automate this so that you don't do what Bob does, we came up with about 15 metrics that we have to use. I don't know what I'm doing wrong, but anyways, here's the top is the deconvolved signal. You can see the second one is the deconvolved signal superimposed on the original signal, so you see the shock pulse there. The third one is the difference between the two, and again, be aware of the scales on the side and then if you cross-correlate those, you get the two cross-correlations at the bottom. Because they're both in phase, they're both positive cross-correlations. The only reason we put this in there is because it's like a textbook. It's as good as the model, and it shows you some of the metrics, which I'm sloughing off on.
Oh, just 1 minute.
Yeah.
1 minute late.
1 minute?
Yeah.
Oh. Okay.
Yeah, well, boy.
Okay, the wizard code is what I did interactively for years. The batch code is taking these metrics and going in there. So let me get to here. Here's the comparison of the wizard code. Again, that's what I do. The batch code is what my team has put together with metrics and all that. And here is an example. We picked an example at NTS. We know the depth, so the depth is 600 and some meters. The waveforms on the left, the log spectrum, the thing. And when you go through these metrics, and the product, as I showed it, the first one, the product of the metrics gives you that the delay between the little p, big P is 0.4 of a second. That's much better than what I do by trying to, my wizard code is what I work with in the middle. And you can see that's much more complicated than what the guys have put together on the right. And if I can just do, okay, this is an example of this. The top is a deconvolved signal, taking out the little p, big P. The next one is the original signal in red and the deconvolved signal. And you can see how, and then the difference, which is an estimate of the little p, big P, is a third one down there. So you can see how the little p, big P sticks up in there. But my criteria is they got to be identical until where I filter them in the Kepstrom domain, and then I see a difference. And then the next to the last one down there is putting them together and then cross-correlating them, and you see that the cross-correlation, the real signal with the deconvolved signal is almost unity, and the original signal with the deconvolved, the different signal, which is a little PB, is almost -1. So it works beautiful. This is what I worked over for years on, and this is what the team has automated with all these metrics and stuff. So let's see if I have a conclusion. And this is a comparison of the same event. This is a event at NTS seen in Norway. And this shows you how the statistics compare between the two, the batch mode, which is the automated mode, and what I do, the wizard mode. And in summary, we've come up with these evaluation metrics where we are able to get for good signal-to-noise ratio and not so good signal-to-noise ratio. And we now have the batch mode almost automated, and this presenting it here is one of the last steps to where we put it into the system so that when an event of interest occurs at home, we can run the program to locate the event, estimate the yield, and in parallel run the depth and then take that into account in the yield. So sorry I had to go so fast. I will be there for these posters later in the day, so feel free to come talk to the team and we'll answer whatever you can. Is there any?
Thank you, and in the interest of time, I think we take the recommendation to meet with the poster. Speaking of posters, now we move on to the poster presentations, now until the break.
Sorry. Well, in our plan it's today.
First 30 posters.
Wow. So we have conflict of application and program and own program. So they are not ready.
Well, they should be because they've been put in a folder. But we'll see.
I have a short announcement about the poster session. I did it in the morning, but it was a different audience maybe. So the posters are in the areas, but the poster authors should be present for this session 3.5 tomorrow, yes, the Thursday from 4:30 to 6:15. So this is the time to present posters, as the organizers say. So it's fixed now for visitors of the posters if they want to find authors. Thank you.
Also, this is a very warm room, and there is some water up here if you find yourself a tad overheated or just need a little hydration.
Sorry?
Says 2. Yeah.
So then we can leave, I think.
We need a line up.
I think organizers know what to do. I mean, better than us.
I'm fine with that.
Maybe.
I'm actually poster 1, so I know where I need to be.
Ah, you also have. Okay. So they are in the line. Oh, I'm sorry.
Okay, I am Kevin Muse, and I'm presenting poster 1 on behalf of Dr. Glenn Shadeen and myself. For those that work with radionuclides following a nuclear detonation, realize that the nuclide production and loss terms are of critical consequence to be able to identify them accurately with the fidelity needed to provide the answers. So that typically means a series of production abatement equations that we have to use over a period of time where there's interdependencies between the production of one set of isotopes as the consequence as a result of a loss of the other isotopics. So Dr. Shadeen and I, most of Dr. Shadeen, giving Glenn credit where he deserves it, did the vast majority of an on-the-fly approach using the Runge-Kutta-Fehlberg solution methodology that takes a variable one step with error control to maintain a target residual error. The idea is that you can work towards a residual error that cuts you down significantly from the number of complexities involved with it, and it takes away some of the numerically stiffness of working with the PBs. We take a look at the RKF methodology, and it seemed to work very well in our proof of concept. Please stop by poster 1 and take a look when you have an opportunity. Thank you.
Good afternoon. My name is Said Sultani, a PhD student at International Institute of Earthquake Engineering from Iran. What we have done actually is using a new stochastic method named self-fuzzy self-tuning particle optimization for calculating a new velocity model using local earthquakes data. We tested this method both with synthetics and real data sets, and in the real data set we compared our final model to the pre-existing model in northwest of Iran, and the final results are actually showing a comparable reduction in RMS, horizontal error, and also depth error, which is actually variable. So, and I would like to invite you to visit my poster. Thank you.
Good afternoon. Thank you. My name is Hisham Sailani. This work concerns the problem of separation of seismic, the seismic signal processing. Indeed, excuse me. This work concerns the seismic signal processing. Indeed, its goal is to estimate the seismic unknown seismic signals known only their mixtures provided by sensors. Unlike the existing approach, which treat the mixtures globally, this proposed local approach consists at the treatment of signals locally and suppose only that the sparsity hypothesis. Thank you.
The Pinedale, Wyoming International Monitoring System seismic array is located in a region with limited useful natural seismicity for crustal reflector depth estimation beneath the array. Knowing this structure is important for event location corrections. We apply seismic interferometry to continuous waveforms recorded at each element of the array to extract reflection Green's functions from autocorrelation stacks. To meet our greatest challenge, which is distinguishing between P and S reflections and identifying the observing Green's function arrivals, we have developed a new method using the F statistic and three-component waveform polarization. If you're curious, please come and visit our poster.
Good afternoon. In this poster, we will show some of the applications we have done to the SISAN software. SISAN is a software you can use to analyze explosions and earthquakes. There's a number of NDCs that is using the SISAN software. So for the future, the CTBTO will now improve the integration of SISAN with the IMS data, and it's been done with the support from the European Commission. So please have a look at the poster. Thanks.
Good afternoon. My name is Amy Sundermeyer from Sandia National Laboratories. Our research is focused on using waveform correlation to reduce the amount of time that IMS network analysts have to spend looking at earthquake aftershock sequences. Our method is shown in the timeline. 12 hours after the main shock, an automatic catalog becomes available. We make waveform templates from those automatically created events, and then we use those waveform templates to run correlations over the next week to see how many events we can find that the analysts had to build by hand. And our results are shown in the table for 3 aftershock sequences chosen by the IDC as particularly interesting. And that estimate of workload reduction is based on the number of events that were not in the automatic catalog that were found by waveform correlation that the analysts had to add to the reviewed event bulletin manually. Thank you.
Good afternoon, everyone. My name is Safida Azimi. I'm a PhD student in American University of Iran. One of the most important interference in radio xenon spectra is lead-214 that decrease the accuracy of analyzing result. We used advanced machine learning methods for activity classification and discrimination from each other and from lead. I will be so happy. See you there. Thanks.
Good afternoon. My name is Tormod Kvarn. I'm working at NORSAR. We are presenting results from a study we have been doing also to address the problem of aftershocks. This was the method that was proposed at SnT 2017, and we are currently also working with the PTS to evaluate the performance of this method. What you see to the left there is the 3,900 REB events located during the 7 days after the Tohoku earthquake, and to the right you can see the 65% of these are taken by this fully automatic method. So the next step now is to evaluate the accuracy and the sort of distribution of this system. So this is something we will continue to work on. So please come to our poster and we can discuss the details. Thank you.
Good afternoon. My name is Ondřej Tichý. I'm from Czech Academy of Sciences, and on the poster we study the influence of real-time concentration measurement, which was invented in our National Protection Institute. And we study the influence of real-time sampling on Bayesian source location and source term estimation. And we demonstrate the results on the case of ruthenium release in 2000 17, and we show that it can better temporarily locate the source term. So if you want more details, you can come to our poster and discuss. Thank you.
Hi, I'm Chris Young from Sandia Labs, and my poster is about comparing two different methods for detecting events using the same high-quality data set from Utah. One is a PIC-based method, so that would be more like GA, and the other one is a waveform back projection method, so more like NetVisa, though it's not Bayesian. And we found some kind of surprising results in terms of what these two methods have in common and how they differ, so please come by the poster and I'll tell you more about that. Thank you.
Hi, my name is Rob Forrest from Sandia National Labs. My poster is on detecting low magnitude seismic events using a particular convolutional neural network method that's kind of an established method. We use this very well-groomed Utah data set to look at low magnitude arrivals. And we find that using this method can actually double the precision relative to established methods like STA, LTA. So if you'd like to know the details, please come by and discuss the poster with me. Thanks.
Hello, I'm Doug Dodge from Lawrence Livermore National Lab in California, USA. My poster describes an experiment with generalized likelihood ratio test detectors used to explore mining-induced seismicity at a Utah coal mine. The processors are based on an earlier software system we've built called a dynamic correlation processor, which can build templates on the fly. And by suitably configuring the spawning policy of such a detector, you can create a generalized likelihood detector. What I'm showing in the plot is just the relative performance of the GLRT detector, which is labeled DCP there, to a correlator in terms of its ability to detect at low SNR without detecting on non-target signals. So if you're interested, come by my poster 25. Thank you.
I'm Noriyuki Kushida from CTBTO IDCSA. IDCSA has been developing software called NetVisa, which is the next generation waveform event detector based on Bayesian inference. That means this is a kind of supervised machine learning. So in this study, we try to use the learned model to other applications such as the event validator. This means we want to check if an event made organized by another application is true or false. And the other application is that we want to synthesize, create artificially on a computer using the machine learning models. And as a result, the results show the promising result. And if you are interested in, please come to the poster P32 for further discussion. Thank you.
Same person, still from Sandia Labs. So this poster is about two very high-resolution catalogs that we're trying to make available to the research community. We've done research on these. So one is from the IMS network and the other is from a network in Utah. And these are painstakingly constructed. I'd say over 8 months spent on each of these catalogs. So I would offer them to anybody in the community that's interested in working on event detection, signal detection, possibly even things like event categorization. These are great data sets for you to use, so please come by the poster and I'll tell you about them. Thank you.
So poster 37 is about INSPIRE project. INSPIRE stands for Integrated Radionuclide Analysis Platform. And this is a way to modernize the IDC software to unify the tool for noble gas and particulates, to also unify the NDC box and IDC, but also to move 100% open source. So the software has been extensively tested by IDC analysts, and now we are in the process of implementing the very latest module, and it will be ready for deployment in IDC operation, but also delivered to national data centers by Q4 this year. So again, poster number is 37. Thank you.
Good afternoon. My name is Hee Lee. As a Korean NDC, our institute is in charge of one IMS station, KSRS. In addition to that, we are operating one large infrasound network, consists of 9 infrasound array stations. In daily routine, we have detected many infrasound signals came from a Japanese volcano, as well as Russian volcano. Over the past 10 years, Tokyo Volcanic Ash Advisory Center issued more than 10,000 warning issues on the Japanese volcano. So I have analyzed all the data, and over the year 2011 to year 2016, with the stress to the Sakurajima, I have processed and detected how the change the celerity and azimuth according to the season. We have compared with the calculated, it means predicted arrivals by using ECMWF model. It fairly well coincident with 2 results. Also, you can see some strange signal when sudden stratospheric warming occurred in winter times. Okay, thank you.
Hi, my name is Takeshi Muramoto. I'm a PhD student in Japan, and also I was intern at IDC CTBTO. Our research focused on spectrum analysis for beta gamma coincidence measurements. We have 2 posters. One is about net count calculation equation resolved by matrix operation, and another is about the non-negative priori was used to estimate interference correction. From these results, there are no decision threshold underestimated, and also false positive detection are reduced. Please visit our poster. Thank you.
We apply Melkepstrom, a technique used initially for speech recognition, to infrasonic events, including bolides and atmospheric explosions. When the right pre-filter is applied, we find remarkable Mel feature consistency at each station and at multiple stations. Although we used a limited number of events so far, promising results suggest that the technique has potential to provide event class features useful for waveform identification and deep learning. If you would like to find some more and to find out why it's different than Kepstrom, Dr. Kemery presented earlier, please come by our poster.
Good afternoon, I'm Dennis Bustillo from General Dynamics. The goal of this project, well, it's part of a larger effort to use existing sensors to analyze them and to make our software a little bit smarter for the RASA operation and control states. In this example, we took the current sensor during a filter advance, and the goal was to try to detect and avoid filter jams, one of the causes of downtime for the RASA. So here we did started sampling the currents at a higher frequency during the advance, and then took the pattern or the waveform of that and applied some algorithms to try to predict when or detect when the filter is jamming, and then tried to take mitigating actions to avoid a filter jam and essentially downtime. Thank you.
Good afternoon. I am Shaban Laban. I will introduce the radionuclide in Sina Cloud. The main objectives of this one is to how to get an offline and remote analysis tool processing for scientific data or sample analysis exchange between peer indices or universities or others. And at the same time, you can have the full capability of the software, both locally or remotely. So in order to do this one, we have to have we have to introduce new things for data product, what we call it a multi-vector sample analysis. So you should have analysis ID for different analysis. At the same time, we are introducing a binary spectrum searchable file, SSF, as a file product that you can put all the related information to process the sample. And at the same time, I'm introducing object-oriented and modular programming. At the same time, a Windows for .NET. And I believe .NET will come sooner or later anyway. Thank you.
Good afternoon. Our poster summarizes the latest relocation studies using ILOC and SnT in Central Asia, the Middle East, and the Caucasus region. We also present some new and updated ground truth information and demonstrate that SnT improves the locations with respect to the AK-135. If you're interested, please come to the poster. Thank you.
Hello, good afternoon. My name is Dirk Rösler from GEMPA in Potsdam. I'm presenting the integration of ILOC as a new locator into SEISCOM-3. SEISCOM-3 is a well-known software for treating earthquakes in real time and also in the post-processing. We have modified SEISCOM-3 to allow you to analyze also array processing results. Those may come from Lambda, which is a new GEMPA module that I'm also presenting, and I'm joining all this together by showing you some results of the North Korean nuclear tests in 2016 and 17.
My name is Mahmoud Sami from National Research Institute of Astronomy and Geophysics, Egypt. My poster is about using deep learning algorithm in order to seismic phase identification, but instead of using waveform data in time domain, we convert it into frequency domain to produce more feature, clear and general feature domain in order to be used by convolutional CNN network. Very simple, and it able to reduce the number of the data training set need to be trained to achieve acceptable result. Also, this model has been used for unseen data for another area. It works also with acceptable result, and even it can work for man-made events and natural event. Waiting for you in front of the poster. Thank you.
I'm Derek Jensen from Lawrence Livermore National Lab.
I'll be presenting work that we've been doing on an atmospheric source term estimation algorithm. At its heart is a dynamically optimized deep neural network that is actually able to emulate atmospheric transport and dispersion models. And we take this algorithm, we test it over literally thousands of different release scenarios, ranging from very, very dense sensor networks all the way down to very, very coarse sensor networks to kind of see how the algorithm responds to that range of data. So if you're interested, please come see it.
I'm not one of the authors officially, but my colleagues have done a synthetic experiment, and for radionuclides, when we say a nuisance signal, we mean medical isotopes. And in this synthetic experiment, which is somehow related to what Chris was talking about earlier, using a Utah network, okay, they were able to identify the location of the medical isotope facility and separately look for a puff release, like an explosion, inside this is all synthetic data, right? But look for a puff explosion that might have occurred inside the Utah network. So a very nice result. And Brian Schramm should be standing in front of that poster.
Good afternoon, I'm Matthias Auer from ISTI. This poster is on the STAX data processing pipeline. And the STAX stands for Source Term Analysis of Xenon, is an experiment. Details of that have been presented by Judah Friese on Monday afternoon session on the radionuclide background. But to briefly summarize, in the STAX project, emissions from medical isotope production facilities are measured in order to associate them to detections at the IMS station, so that the background at IMS station, measured at IMS stations, can be better categorized and it can be associated to industrial background. So this post is about how the actual data processing is done, so more on the infrastructure. So we show here how the data are processed at the station, how the analysis is done, what are the data transfer mechanisms to the central data servers, and how the data can be accessed by users. And also a new data format has been introduced that is aligned with the IMS format, but somewhat differently. So if you're interested, please come to the poster.
Good afternoon, everyone. I'm Liu Zhan from the Thailand DC, mainly engaged in seismic data analysis. And the title of my post is the application of multi-criteria sensitive method in classification of DPRK events. The complexity of waveform, spectral ratio, and sensitivity ratio were selected as the 3 criteria for classification of volcanic explosions from earthquakes. And the 3 criteria and the multi-criteria sensitive method was applied to 6 volcanic explosions and 5 natural earthquakes, which happened in Pinjari nuclear test site of North Korea. The results of the application indicate that that's all. Thank you. Yeah.
I'm Jun Wang, IDC radionuclide analyst. And my poster is the content. From the day-to-day our spectral review. In my poster, the spectra, both the IDC review and the laboratory analysis to show and to examine the false negative peaks and false positive peaks. A brief conclusion are obtained in the complex of small peaks in radionuclear spectra result in the increasing of false negative and false positive peaks. This is specific to CDBTO, Otherwise, interactive software need to be developed. This is the result and the recommendation. Thank you.
My name is Rigo Tibi from the Sandia National Laboratory. What we did is that to reduce the human analysis workload during the seismic event building process, we are proposing an interactive, rather than a linear pipeline, we are proposing an interactive processing framework that incorporates automatic analysis behavior. As the figure of the right show, the framework we are proposing includes all the components of a traditional pipeline, but there's a controller module that we added that we call auto-analyst, which take over many of the tasks generally proposed by human analysts. And test results using 2 weeks of IDC data show that our pipeline or our framework perform better than the traditional pipeline. And most of the traditional the additional event built by our framework are low magnitude event that were missed by traditional pipeline of event building. So the poster will be tomorrow. Thank you.
Hello, my name is Judah Fries. I'm going to be giving an overview of the STACS project that Matthias just mentioned a little bit earlier, talking about the overall goals, what we're trying to do, and how we can use a new data source to help in treaty monitoring by understanding the backgrounds that are released to the environment from large sources. So I'm going to talk about the overall process and kind of how we're looking to implement this in a way that allows data to be used for monitoring, but at the same time still protect the proprietary information of the commercial sources where this is coming from. So stop by my poster. If you ask about the pipeline, I'll send you to Matthias because he knows more information about how that's going. But I hope to see you at 4:30, just in case you didn't. I was confused when it was. All right, thank you.
So there's a growing class of problems that are appropriate for the use of deep learning to build high performance predictive models. But even if we have a highly performing predictive model that we've demonstrated works well on independent data sets, that doesn't necessarily get us to the point where we can use those predictions to help us do things like prioritize analyst decisions. So if you want to talk about different approaches to getting to usable uncertainty for these predictive models, come see me at my poster.
Okay, so in this work, we serve the association problem. So what you have here is simply Markov chains evolving. And in fact, we used a few number of infrasound stations in order to get the correct sequence and the correct number of events. So for each point here, in fact, you have the number of waveforms that are computed. And we use for that a reduced model, which is called flows. So if you are interested by the way we obtain this kind of map, so come to the poster. Thank you.
Hello, my name is Claire Perry with the Canadian Hazards Information Service, Canadian Data Centre. So I'm presenting this poster on behalf of my colleague, Michael Colai. So we are using spectral ratio techniques to discriminate between low magnitude earthquakes and blasts due to construction on road cuts. So we've looked at a suite of magnitude 2 or less earthquakes and blasts in a region of New Brunswick, Canada, in eastern Canada, and we've used the Mahalanobis distance parameter in order to determine spectral ratio discriminants for both PG over LG and LG over RG ratios in order to discriminate between these low magnitude earthquakes and construction blasts. Come see the poster if you're interested. Thank you. Bye-bye.
Do you have 82? No. So I have no more poster. It's more to announce for the coffee break. which will be 30 minutes. So we will resume at 15, quarter to, what? Last one. But it's a different session. Okay, please go ahead. Yeah.
Sorry. Okay, Abdul Wahab from the CTBTU Capacity Building and Training section. Sorry, this is the whole poster because we missed the 1 minute presentation. This is the new training cycle approach, TCAN1, for national data centers, developed by the Capacity Building and Training section. In general, this is, now we have the introductory, intermediate, and advanced courses. So, and each one is prerequisite to the second level. Also, we have complementary trainings like SAISCOMP, infrasound, and also in the same cycle to complete and to fill in the gaps if there are some people who did the trainings before. So this is the new training cycle approach, TCAN1, for on the poster number 44, if you want more details to visit.
Yeah, 5.
So again, coffee break will be 30 minutes. Enjoy.
Thank you, sir. You're not doing anything anymore.
Could we start the next session from 39, just 1 minute? Yeah, thank you. Just to make sure that we have a complaint that it was on the screen, but it not listed because it was supposed only 30 posters during this review session. It's just mistake. No problem. Not mistake. That one. Thank you. 39. Because it's a common issue. Some people did not show up because of they thought it's next review session.
Can I leave my stuff here, Smart? Oh, good, thank you.
Good. Hey, I'm going to the toilet. I'll press all the buttons again. I'll press all the buttons again. No, please don't touch anything.
It's enough for
Copy
sure.
this one.
Yes,
I have to
I
take my bag.
Oh, yeah, sure. But if you go to the back.
No, the copy is okay.
No, I didn't. Okay. Just relax. Need to here and it's familiar with us. Just left.
Take your coffee.
Put the coffee.
Yeah, that's what I wanted to do.
So that is withdrawn, I think. It was in my material. It is this report, yeah? This one, yes. It is withdrawn. That's why we moved to 15 minutes later, because we don't want to have a gap.
Okay.
It just because this too delayed, but this starts on time. So now we have Paul Richards here. It's instead of 30, it's 45. So these two are moved 15 minutes later, but then because this is absent.
Okay. If it's absent, then it makes sense that we don't have this presentation.
Yeah, you don't have it because it's. I'm sorry. So you don't have that information. I'm sorry.
No problem, sir. Thank you.
Yeah, it's strange. So nobody knows what happens. They don't have information about the withdrawn report talk. So. We start with Paul Richards because we don't give any preview session anymore. Oh, it's time, I think, to start. Yeah. It's a couple of minutes. Paul comes and. Okay. So you introduce?
All right, so we'll go ahead and get started. Coming back a few minutes late from the break, but good news is that topic 3.5-06 is canceled, so we'll put us right back on schedule once we work to the 1700 timeframe. So we'll start with topic 3.504. Can high precision methods of seismic monitoring for earthquakes and explosions find application for broad areas?
So, ladies and gentlemen, you see the title is a question, and my whole abstract could be summarized in the one-word answer, yes. Let's see. I probably need to press something, yes. So I have to give this talk in 4 parts. Some of it, the background material in particular, some of you will have heard before. The objective is really so very important because a list of seismic events with high precision is the starting point for research as well as for treaty monitoring. For so many different activities, for understanding the physics of earthquakes, for understanding the relationship between seismicity and tectonics, and so on. So for a number of different research communities, achieving radical improvement in the precision of locating seismic events and driving down the detection thresholds to lower magnitudes really is something that the whole community is, I think, interested in working on. The background on this planet currently are documented on the order of 500, 600, 700 seismic events per day, not really accounting for the vast number of seismic signals from blasting activity. And numerous studies have shown for small areas that there is the opportunity for vast improvement in the precision of event locations if we walk away from the main framework in which bulletin production has been done for more than 100 years. Going back to 1912, the concept emerged in Germany of using phase picks at a number of stations and interpreting those minimal sets of information in terms of somebody's travel time model. that's a good start. And there's always merit in ever more improving three-dimensional knowledge of the Earth's structure for purposes of getting a better and better interpretation of observed arrival times. But in my opinion, the quality of being able to measure careful arrivals, or relative arrivals in particular, is today so great for neighboring events that there is a path forwards to high precision, at least for a significant subset of seismic activity. So I will be describing some prospects in Mongolia, but first I have to go back to the background, including a presentation of work published, some of it just last year, but presented, some of you may have seen some of these graphics before. I plan to describe a couple of different projects. First of all, to achieve detection of lower magnitude events using archives of events already known, and then later to talk about high precision locations. So the events you just saw, those red points, were LEB locations. They're typically a few tens of kilometers, not quite in the right place, but I'm making some pretty strong claims here, and the context in which I think this work will be done is over the next 10 to 20 years. I'm not talking about something that's going to be done next week. I think it needs to be done by a team that has competence, ambition, and resources, and we don't have such a team at the moment. So, just to show an example, work done by Megan Slinkard and others, published already, aftershocks of the Wenchuan earthquake. Here they are as reported in the LEB in purple dots. At that time, there was a Pascal deployment called the SnT program in the neighborhood, and to run the 1400 waveforms recorded by the stations you see here shown in yellow through the continuous data reported by these stations for several months was to produce a set of detections shown in red, and as we reported here 2 years ago, much greater, in other words, a factor of about 5 times more events than show up in standard bulletins. So the events shown in light gray were templates searched through continuous data to get the darker gray events, a factor of about 5 or 6. So then the other aspect of radical improvement, not only to detect at lower threshold using templates, but then to achieve improved location. Let us look instead at the small box west of Beijing, and clusters within that box, work done a few years ago, shows that for a set of 10 events, their relative location can be estimated by using cross-correlation applied to pairs of waveforms of neighboring events recorded at a common station with millisecond precision, or a few milliseconds, I shouldn't exaggerate, on the order of 3 to 5 milliseconds is possible with high-quality recording, in particular of the LG wave. But then for clusters of events that are so close together already that their LG waves are highly similar, the relative arrival time of neighboring pairs of events and their waveforms recorded at common stations can result in precision of location, as you see it here, quite remarkably, a factor, when this can be done, well improving over a factor of 100 upon traditional efforts of location. The key is to walk away from the traditional idea of how you do location with impulsive phases like the P wave. We prefer to work with a really nasty-looking, boring kind of wave with no impulses at all, but it happens to be typically one of the largest regional phases, the LG wave. It has a high time bandwidth product. And in a study published last year, for a 21-year period from 1985 to 2005, including those years, 21 years, about 18,000 earthquakes in China and neighboring regions, with signals recorded at over 300 stations openly available through the IRIS data system, were made 111 million cross correlations to find a subset of about 20% of those 18,000 earthquakes, whose relative location can be determined remarkably well. Let me hustle through this short talk. Necessity is short. In red is shown 64 clusters where 7 or more events are really close to each other, and it becomes possible, for example, with a cluster, as you see it in the middle, reported, the scale there is a map of plus or minus 10 kilometers northwest, east, north, south, east, west. When studied with their waveforms recorded at common stations, the cluster collapses to the point you see in the left-hand map, which has a lineation with it associated with an appropriate choice of fault plane and a focal mechanism shown on the right. And then if I go to the next graphic, another cluster, for the same cluster, here is shown that expanded view of the same cluster with its lineation like one of the fault planes shown in that focal mechanism. But most remarkably, in that right-hand side are the confidence ellipses associated with these events. They're just incredibly small. And we had a year-and-a-half tussle with the reviewers doing their job, criticizing our paper because they couldn't believe at first these low confidence, those small-size confidence intervals. Another cluster, in this case, as you see here, 27 degrees north, nearly 4 degrees east. The same concept. In the middle, a group of, I think it's 9 events located by traditional methods. They collapse to the cluster you see on the left. It has a lineation associated with what you might choose then for one of the fault planes. And then when we expand the view of that cluster of 9 events with a different scale for the map, and then they have this remarkably small confidence intervals. So that's not possible everywhere, but with a very sparse station set, this is the kind of thing that is achievable. So to summarize these results briefly, we have about 20% of the events work out really well, and many people, I would say on the order of 100 groups, have worked through this since this type of analysis began in Iceland in the 1980s. 6 steps of finding templates, of running them against continuous archives, of identifying new events, of measuring relative arrival times, of neighboring events recorded at a common station, and then massively validating those detections and getting their relative location. This can be done and has been done by numerous workers. Many of you in the room have demonstrated this on the small scale, but can it be done for broad areas? I'd like to do it for a really big network, but maybe that will happen one day. But currently we're focusing on Mongolia, a country which had 3 magnitude 8+ earthquakes in the previous century, and their aftershocks continue today. A country which has massive mining operations and associated blasting. And in the dark green band here is shown a region of seismicity which we're currently studying for the continuous 5-year period from 2012 through 2016, that is 5 years in total. And at this point, I should say that we should have added 2 more co-authors to this paper, Amy Sundermeyer and Megan Slinkard. I surely hope and expect that they will be authors of what we eventually publish on this project. Their contribution from Sandia was essential to what I'm describing in an effort that's gone on now for more than 8 years. We have worked with, on the order of, I think it's, got my notes here. Yes. So we have worked with, on the order of more than 10,000 LEB events over a time period longer than 5 years, and have searched the continuous data at the 9 stations shown on this map, to find on the order of 10 times as many events, which we would regard as being validated. And we find ourselves in the situation, having been very careful, Amy Sundermeyer in particular, being quite sure that we worked with high-quality templates with a signal-to-noise level of 4 or above, leading to, yes, many additional detections, but there needs to be the detection at enough stations to achieve location. So we are now at a stage where we have about 10 times as many events, and we need to make a segmented data request to additional stations that we anticipate will provide the necessary number of additional measurements of delta T to enable relative location. So this is a progress report. I'm happy with the progress. This is the last diagram. It shows the fraction in red of events that can be located currently, but it's not the full story because we need more stations to provide measurements of delta T to enable that last step of getting relative location for the 10 times as many events that have already been detected at high-quality stations. So this is the summary status. The surprise is not to use impulsive ways, but to use LG. This is a big data method, and sociologically, I will make the point that this is a project really too large for your traditional academic effort with some guy called a professor and the people who do the real work and a couple of graduate students. That's absolutely been a satisfactory team for applying these methods on a small scale. I just really want some major data center to have the ambition to make this work on the large scale. We're doing it slowly, but I think that in future decades, this will be the major big data aspect of seismology. And thank you for the opportunity to tell you about it.
Thank you. We have time for a question or two. Is there any in the room? If not, we can go ahead. Oh, we've got one here.
I have a question about the number, which is 10 times more than LEB. What kind of events you mean? LEB ready events, so same quality as LEB with the same parameters as LEB event, or it just...
No. Let me thank you for the question. We are talking about a subset of detected events, and I well recognize that agencies charged with monitoring must continue. They're valuable to continue with traditional methods because our method only does its good work on a subset of all detected events. But then to answer your question, we have confidence that we have detected about 10 times as many events. It's actually more like 12 times as many. They don't have impulsive arrivals for the P wave, or we haven't even bothered to look in practical terms. We're talking about data sets so large you can't look at individual seismograms. But yes, the LG wave cross-correlates for these newly detected events very well, and if it is time reversed, you don't get a detection. That's one of the methods by which we can set a false alarm rate and so on. So this is 10 times as many detectable events, and their quality is much lower than the data in the LEB, but it is adequate to achieve a high-quality location.
Okay. Thank you.
Oh, sorry.
Well, there's one more question.
One more question.
Yeah, Ronald Brazili, CTBTO. I was wondering if you have any way of estimating the magnitude of those events.
Oh, yes. Yeah, so the simplest way is to use a non-normalized cross-correlation against the template. So one can say what the magnitude difference is from the templates that detected it.
Okay. Perfect. All right, well, let's move on to continuous assessing of the reviewed event bulletin with waveform cross-correlation.
afternoon. So we named our presentation as continuous assessment of the reviewed event bulletin with waveform cross-correlation. Since 2008, there were many tests and experiments at the IDC showing that applying cross-correlation may increase the number of the RAB events significantly, and at the same time we can reject many RAB events. And the main idea behind this presentation is that continuous comparing of the event hypothesis of the RAB tests against historical events at the IDC database may improve significantly RAB quality and consistency. In this presentation, we'll highlight a little bit our product that we are going to release soon, which we call SpotCheck 2, based on the cross-correlation master event approach, and describe its different modes, automatic, interactive, and describe a little bit its architecture. So it's more or less technological presentation. We're not touching cross-correlation details because there were rather many presentations and papers about this matter. The spot check is aimed at the improvement of the RAB, and it's considered as a final level of the interactive review hierarchy, and it's also called independent review. It provides extended check of the bulletin and identify both consistencies and inconsistencies of the RAB. The reviewed areas where we apply the spot check tool, spot check technology or spot check tool, includes event location anomalies, seriously mislocated events, missing large events, etc., and also the events which are not satisfied to the event definition criteria of the IDC or EDC. Both teleseismic and regional distances are embraced, and natural man-made sources involved, and we apply this technique both to seismic and infrasound technologies. We started SpotCheck tool development as cross-correlation approach was very good showed itself during many years at the IDC. And underlying technology is waveform cross-correlation with the master event approach. And at the moment, SpotCheck tool works in two modes. I would say the SpotCheck prototype works in two modes, and SpotCheck tool is a continuation of the prototype development. So in interactive mode, independent reviewer can tune this tool and provide his own scenario, his own settings to for searching the events. And in automatic mode, it works on a daily basis, 24 hours a day. It builds so-called XL or cross-correlation standard event list, and it conducts automatic comparison between cross-correlation bulletin and or signal list, event list with RAB or standard event list. This is a generalized structure of the SpotCheck tool. It consists of the IDC database that supplies actually the data to it's the source of the data. It's a cross-correlation pipeline that includes cross-correlation based detection, local association, event characterization, and the templates can be used by the SpotCheck tool can be just real templates that just regular waveforms, PCA-based or principal component analysis-based templates or subspace based on subspace detector, and just purely synthetic templates for the areas for the aseismic area. We cannot build subspace templates. At the moment, there are about almost 500,000, more than 500,000 RAB events that can be used for templates for the SpotCheck tool. And more than 100 new RAB events edit every day. So this tool should involve online population of the master event database with the newly determined master events. Master event selection is based on several principles. One of the principles, we divide the globe by one degree cell, and if it's enough events within each cell, we cross-correlate each of them and find the best master event. If that's not enough events within this cell, we just select the best RB, we call it the best master event, with a magnitude less than 5, MB less than 5, with enough phases or stations. And for both approaches, we also scan by depth with a step of 40 kilometers, scanning the depth from 0 to 700 kilometers. This spot check tool works on as a parallel software, and each process is attached to the seismic region. So division of master events by seismic region makes sense because it's expressed predominantly tectonic regime and geology, so source mechanisms and propagation characteristics matters in this approach to our opinion, and such master events are likely representative and quite efficient in the spot check tool search. This is an example of the input of each station for each seismic region. You can see on horizontal axis it's seismic regions from 1 to 50, and vertical axis at seismic stations. You can see that some stations like Eiler, Varamunga, ASR populates very good to most of the seismic regions, while some stations like Kest and other populated just to few seismic regions. And this is why the fusion officer or the reviewer in his settings can check which station he wanna use, not to waste the resources of the computer if he analyzes, for example, some specific seismic region, not the whole globe. As for the subspace template generation, we consider the data not just only as a single component data, one-dimensional data, but as a multidimensional objects. For example, each sample of the seismogram, of the three-component seismogram, can be represented as a hypercomplex number, for example, like a quaternion. And building the hypercomplex matrix, we can apply hypercomplex singular value decomposition and create multidimensional templates, and then we can compare the multidimensional templates with the multidimensional traces. And same for the arrays, but in this case we consider it as a tensor. So single vertical component, for example, is just a 1D tensor, while the three-component seismic array is a 4D tensor. And applying 4D or 3D SVD, we can provide the array template, multidimensional array template. And such approach showed pretty good results, but so far pretty limited experiments. The diagram of spot check 2 is we have raw data populates IDC database. Then IDC database populates cross-correlation database. With a subset of this database is a qualified master event database. The waveform cross-correlation pipeline starts working, provide detection, association, conflict resolution, and in the end create the Excel cross-correlation bulletin. And it's automatically compared with cell or retrospectively with REB. If the new master event is detected, it automatically populates the qualified master event database. If upon completion of the comparison, there can be a case that the new 2RB event is created, and then it goes to machine learning and provides some effective procedure to be sure that it's a new event and not just a bogus event. It can be matched, RB matched event, but it can be a case that we cannot find the event that was in RB. And in this case, it goes to automatic spot check involving a library of wide range of adaptive adaptive methods, and involving more master events that is just basic master events for the for automatic spot check. Because in automatic mode, we cannot provide too many comparisons with too many templates due to just computer resources problem. And if even in this case we cannot find a new event, we cannot confirm the new event, that it goes to the interactive spot check tool where reviewers apply his sophisticated procedure, doing his own tuning, applying new parameters, adding new templates, for example, using not just 12,000 event, but 100,000 or 200,000 event. Based on this approach, we created the architecture and the software with the information backbone. It's a historical IDC database. The front end of the software is a LifeRay portal. It's IDC, current IDC portal. And a computational backend is a distributed infrastructure with the servers and workstation. And we are going to migrate to GPU servers soon. So as I say, the front end is LifeRay, and it provides also the framework for the future expert technical analysis special studies applications. This is not fancy interface, but anyway, it shows the basic method of the spot check analysis using just origin ID, just provide origin ID and creates a list of the events and show if this consistent with the RAB, if Excel is consistent with the RAB searched by time and date and by latitude, magnitude, and so forth. And it shows that how many settings you can do with this pick specific seismic region, specific stations, what kind of master event you want us to select, natural, subspace, or synthetic. And this is the result of the spot check tool. You can see the RAB event that we want to check at this moment. We can see the nearest master event, and we can see the slave, which is the solution of the cross-correlation procedure. And the bulletin you can see also in the same screen. So there are some additional feature that allows this infrastructure, this architecture to apply it to the expert technical analysis. And this is expert technical analysis procedures with Jupyter as a journaling. So in conclusion, can say that we developed the architecture for the spot check tool and provides flexible interface and not only a fusion officer or lead analyst, but also authorized CTBT community can use this interface. It provides a tool for expert technical analysis, allows adaptive mechanism, and so it's most of what I want to say. Thank you.
Thank you very much. Yeah, I believe we have time for a question, if there are any. There's one right there.
Thank you, Mikhail, for your nice presentation. Just one question. Do you use only earthquakes as your master events, or use also explosions as master events? Because the purpose of the spot check is to find, actually, one of the purposes is to find missed events. I want to know whether it is possible to find only earthquakes, or it is possible to find explosions as well.
We used, for example, experience with the DPRK when we have several templates of the DPRK, and thus we were able not only to improve the location, but also to find a lot of aftershock from the recent explosions. And based on this spot check tool, Ivan, he's monitoring all the time and seeing aftershock from this area, which is based both on the explosions and on the aftershock recorded previously and confirmed by analysts of the IDC.
Just extension of the answer. We use the whole bunch of historical waveforms from nuclear tests to create synthetic templates, which are used to run for the globe as a synthetic master events.
Mm-hmm. Okay, thank you for that clarification and answer. Subject to any other questions, I recommend we move on. Looks like we got one more real quickly.
Yes, thank you very much for the interesting talk. I will ask the same question that I'm always asking, and I'm still a little bit puzzled. I understand that the Excel now is a product, so can we see this Excel and to learn and to see the data? Okay, is it published or it's not publicly available, the Excel location, the bulletin?
This is probably the question to Ivan, because...
Yeah, it's a prototype, so right now there is no calculation because we have different tasks and the computer just one. So we have to kill all Excel production. It's not our fault, it's because we have many duties. But we are going to provide the full Excel when it's available for the states parties through mechanisms which are usual for that. Thank you.
Okay, for those of you that are just, thank you very much. For those of you who are just joining us or tracking the schedule, we're canceling topic 3.5-06, so we'll move forward with -07, the identification of repeating seismic events using diffusion maps.
So, good afternoon. I will talk about application of diffusion maps, a machine learning technique to identification of repeated seismic events like aftershock sequences. First, I will talk about motivation and algorithm. Then I will show several case studies, including aftershock identification and local and regional distances, quarry identification, and also I will show how this technique can be used for verification of waveform correlation detection at a single station. So, automatic identification of seismic event clusters such as aftershock sequences will help to lighten the analyst's burden. In our approach, we consider the seismic event identification as a machine learning classification problem similar to face recognition. You know that if your image, your face is on Facebook, the Facebook knows to recognize you to other images. So we would like to use well-established image processing technique in order to achieve something similar. If I know main shock, I would like to recognize as many aftershock as I can. So, at the first step, we have to convert seismogram to image. Here on the top, you see two seismograms. The first one is the main shock of the earthquake in the Dead Sea area with magnitude 0.52, and the next is a seismograph of its aftershock with magnitude 2.6. Maybe you know C, but it's clear that the amplitude differences are huge, about 6 orders of magnitude. If we use standard spectrograms at the middle, you see that the images are very different. So it's very difficult to compare them. We use the technique of sonograms, which just summarize the spectrogram at the frequency band, logarithmically scaled frequency band, and then we make normalization by every frequency band. So in the bottom, you see two normalized sonograms, which now looks a bit much more similar. So this is technique which we use at the pre-processing stage. Next, we use diffusion maps, which is nonlinear dimensional reduction technique. In order to understand the idea, I would like to mention that if the underlying structure is nonlinear, usually the linear dimensional reduction techniques like principal component analysis does not work. For example, you see the Swiss roll, and if you apply the PCA, we cannot distinguish the colors. On the other hand, the diffusion maps easily distinguish the color. So the diffusion maps are unsupervised technique. It does not use the data labels. It constructs global description of the data set from local similarities. Actually, it uses eigenfunctions of a Markov matrix. And for us, it's more important that it preserves the distances of the original data by defining the diffusion matrix. That means that close points in the original space remain close in embedded space. So if normalized sonograms was similar, it continued to be similar also in reduced space. This method was introduced by Kaufman and Lafon. I will not describe it, it's well described in the literature. So now our basic processing technique. We start with seismograms, we convert them to the normalized sonograms, then we apply diffusion maps, and post-processing stage, we apply thresholding of nearest neighbors classifier. Some features of our method. First of all, we don't need templates. We use only main shock of only templates. I think it's the most important feature of this method. For example, cross-correlation, as you know, need a lot of templates. Input for our method is arrivals at a single station. It may be detected by ST-LTA, cross-correlation, or some other method. Processing, we compute normalized sonograms and then the diffusion maps. And for decision, we use first diffusion coordinate. And output is a list of identified aftershocks arrivals with associated score. So first example, aftershocks of Dead Sea earthquake with magnitude 5.2. As a data, we used 1 week of continuous waveforms at one of the vertical channels of IMS array Mount Meron in Israel. We applied standard filter, Butterworth filter with corner frequencies from 1 to 5 Hertz. Then we applied ST-LTA detector with threshold 3.5. And as a result, we have 98 detection, which was input for our algorithm. And when we applied our method, we identified 51 aftershocks. 18 for them were new, not included in Israel National Catalog. Moreover, the underwater explosion collocated actually with main shock, you see it has very low scale. That means that this method is not locally specific, location specific. Here also we show that this method can be used as verification tools of correlation detector at the single station. We make some exercise. We took one aftershock with magnitude 2.6 and used it as a pattern and applied it to 2 days continuous waveforms with very low threshold of 0.4. We received many detections, namely 442, and now the problem how to recognize which of them are real aftershock and which are just false detection. Oops. So here are results of our method. The diffusion maps score easily distinguish between real detections and false detections. Here's an example of earthquake at the regional distance. We use Crete earthquake. As the input data was 2-day continuous waveforms at Eilat station, a distance about 1,000 kilometers. LEB catalog included 33 aftershock with arrival of this station. So we, as an input, we use arrivals of IDC automatic detection table, which included 216 events. And when we applied our method, actually the real aftershock were detected, also included some aftershocks that were not included in LEB catalog. Also, this method can be used as a quality measure in order to recognize the false association. So here's an example of application of this method for quarry explosion classification. We use 5 quarries in Israel and Jordan, and the results was 85 correct classification rate. Summary, we introduced a new diffusion map-based method. The method was successfully applied to aftershock identification and quarry explosion classification. The method can also be used as validation tool for waveform cross-correlation to exclude the false correlation detectors. Here is some of our publications. Thank you.
Thank you for that interesting talk. Are there any questions on this topic? There's a couple up here.
Thank you for the presentation. I have, I think, a quick question. In your post-processing stage, you run a classification, you run some classification. So I want to ask, is the number of classes predefined? Is it like 2 aftershock or non-aftershock, or is it?
Actually, we have 2 classes, aftershock and not aftershock.
Okay, thank you.
One more right here.
Are you using Euclidean distance in the against the diffusion maps?
What do you mean inclusion? We use diffusion maps in order to reduce the dimensionality. So we use only one coordinate in diffusion mapping.
Oh, okay.
Actually, the technique is described in our latest publication in Seismological Research Letter.
Time for one more quick question if there are any. If not, we'll go ahead and move on. Thank you. Up next is the machine learning for emulation of seismic phase travel times in 3D Earth models.
Good afternoon, everybody. Over the past about 10 years, my colleagues of mine and I at Lawrence Livermore National Laboratory have developed a series of three-dimensional Earth models that we've primarily started to use for predicting travel times. Those models are freely available and along with a code to compute travel times through it, and those are used by a number of researchers around the world. One of the comments from operational monitoring agencies and others who would like to use it more routinely is that the computation of the times would be more useful if it was done faster. And that is where this work comes into play, where we're trying to use machine learning to emulate the output of the 3D model just to simply make it faster and potentially to make it more useful. Before I go into the emulation, I just want to review some of the effectiveness of the 3D model. I won't go into the 3D model in great detail, but that panel in the upper right is a cross-section through the full global 3D model, and you can see some rays traced through it. And then in a 2015 publication, we went through how much the 3D model improves travel time prediction. And these are just a couple of figures. In the lower left, it's distance out to 100 degrees, and these are P-wave predictions. The red, or the black, is the standard AK-135 radially symmetric model residuals. And you see here at regional distance, the bias is pretty big, and the standard deviation is also pretty big. At teleseismic distance, it does pretty well. But with the 3D model, we pretty much remove the bias at all distance ranges and significantly decrease the spread. These bars are 25th to 75th quantile ranges. And then this is just another way of looking at the same thing. We've just taken the mean absolute deviation of the residuals, and this is AK-135, and the 3D model showing that our improvement is upwards of 70% regionally and about 40% or so, maybe 30% globally. How does this play into event location, which we've seen a lot of? This is another part of that 2015 paper, and these various figures just show, for instance, on the top here, upper left, that is the average location error just for teleseismic P waves. So again, AK-135 is this black line. You get average locations. Once you get enough P picks, this is P picks out to 100, of 7 or 8 kilometers, that's reduced down to maybe 6 kilometers after you use the 3D model. And the improvements are even more impressive for regional phases where AK-135 is upwards of 10 kilometers, and then because the biases are so bad, the more data you add, you can actually make the location worse. When you do the 3D model, we're down here in the 5, sometimes sub 5 kilometer error, and the percentage increase just starts off at about 40% and just climbs and climbs and climbs, in this case up to 100 PN picks where we're upwards of 75%. These panels here on the right are perhaps even more important because it shows that when you use a model that has bias, you also bias the event locations. These are just an example of 10 network realizations of mislocation vectors for an event at the Nevada test site. So this is a nuclear explosion. We know exactly where it is. And on average, all of these are biased towards the west or south. When we use the 3D model, the location errors, they're not perfect, but they're much more random. So there's certainly a lot of benefit to using the 3D model, but why don't we use it? And it's essentially because it's too slow to calculate the travel times. For teleseismic rays where things behave fairly easily and the rays are traced fairly linearly, we can compute the travel times in about 1/10 of a second. That's pretty good for operations, but still not fast enough. And then regionally, where this is a source and all of these dots or these triangles here are stations, and each ray here arrives at the station within 0.2 of a second. So there's all kinds of multipathing going on. You've got to do the algorithm to figure out which one is the fastest time, and those things add significantly to the travel time calculation. So it can be 10 times slower to calculate a regional phase than it is teleseismic. I won't go into all the details that we've done, but if you try to put this into an operational system, it just slows it down too much. So there are a number of approaches that have been used to try to make these 3D models more operational. One that we were involved with the National Lab Consortium along with the U.S. National Data Center is the Regional Seismic Travel Time Model. We saw a couple of presentations on that earlier today. It has the advantage of being a millisecond travel time calculation. It's accurate when the regional structure is well approximated by a linear gradient in the mantle. Some of the disadvantages is it's limited to 15 kilometers, so we're correcting that area of the travel time error where the most error is at regional distance, but it doesn't extend to teleseismic distances. You could also take a full 3D model, ours or anybody else's, and pre-compute the difference between, say, a radially symmetric model and the 3D model and save that as a correction surface. Then you just look up the travel time for the 1D model and correct it with this lookup. And this is the basis of these source-specific station corrections that are in use at the IDC now for regional phases, and this is an example in the lower right of, for instance, an SSSC built with the 3D model, but they could potentially be extended to global distance. These can be used with a fully 3D model. That's an advantage. Global implementation has memory requirements. Typically, these things are just implemented as corrections for a surface focus event, maybe mid-crustal. If you wanted to make it 3D, these grids get pretty big and could be potentially difficult to deal with. And also, if you wanted to fold, say, a national data center's network into this, you would have had to pre-compute all of these things in order to really make it useful and make it work with the IDC network. This has been done, the full 3D globe or 3D grid, for instance, for non-lin loc, but that's generally applicable or has been applied to local distances. So moving into the the machine learning part of this, machine learning's been used for many, many things. We're all familiar with search engines and fraud detection on your credit card and all these other things. And they work sometimes better than in other places, but the application of them just keeps growing and growing and growing. Not us, but other people have said, well, if you can use this to predict something, how about if you try to use it to predict the output of a very complex modeling exercise? Sometimes it's weather calculations, or sometimes it's really intense physical calculations. You could do a number of these things and then see whether we can just use machine learning to emulate that. This was so intriguing that the U.S. National Academy of Sciences has written a number of publications on this, and they're paraphrasing their result. Machine learning is essentially a very powerful tool when done right, and this is where the rub is. You can always do something right, but there's a number of ways to do it wrong. So as we started to want to apply this to our travel time calculation, we said, let's go slow. But the fundamental aspect of this is, how are we going to train this thing? We're going to compute millions and millions of travel times at random station and event locations all over the globe, and then we're going to train a neural network on that and validate it. So here we go. The first thing we did is calculate 2 million travel times for random positions all over the globe. When you do that, you get a path length, or a density, array density as a function of path length that looks like that curve on the right. And the reason I put that up there is that you notice short path lengths are undersampled, and that's exactly the area in the Earth where we get the most error. So keep that in mind as you see the first results, but I'll return to that later. So in some of the first tests, just a very simple idea of how this works, you might input distance, and then from that you have a network. In this case, it's a boosted regressor. It's about 1,000 nodes with 10 layers, and you train this, and you try to get a travel time calculation out of it. So our go slow aspect of this is, let's not just go and calculate the 3D travel times right away. Let's see what machine learning can do. So our first test was to just simply see whether machine learning could learn the ellipticity correction of the Earth. The Earth isn't a perfect sphere. Let's calculate the travel times through a spherical globe, calculate it through one with ellipticity corrections, see whether our 2 million number data set can learn it. Our second one was to see whether it can account for event depth. So that's a bit of a nonlinear function at close distances. It gets more linear with distance. And then 3, let's try to use it for full 3D calculation. So you're going to see a number of these, so I'll take a second to describe the axes. Each one of these is distance, 0 to 100 degrees. These are all P-wave calculations, first P. And then these are residuals, but the residual scale might change. In this case, it's -2 to 2. So this pattern that you see on the left is the error that you'd get if you didn't account for ellipticity calculations. What happens when you do machine learning? The training set is shown here in the middle. We reduce the standard deviation from about almost 0.4 seconds down to 0.02. And the training set, a third of the data was left out. The standard deviation is 0.3. So it does a pretty good job of learning the ellipticity correction. Next, event depth. So these are depths ranging from 0 all the way to 660 kilometers depth. You'll see that this is now plus or minus 10 seconds. The big red spot here, this is the range of events in the crust. And then as you get down into the mantle, the errors get bigger and bigger and bigger. Our training set, and this is standard deviation at 27 seconds. So this is a non-trivial correction. So how do we do in the training set? We reduce that to about 0.6 seconds. How do we do in the test set? About 0.17 seconds. So it does a pretty good job of learning the depth correction as well. Moving through it, this is the difference between a 1D model and the 3D model. Now there's 1.8 second standard deviation. The training set brings us down to 0.2. The standard deviation is about 0.6, which is even slightly above what our estimate of the error is for the 3D model, so we'd like to get that lower. So how do we do that? What we did is selected 32 random stations and just calculated a denser training set for each one. In this case, it's here. There's a lot of events right around the station. You can see this density here. A lot of samples regionally, and then fewer at teleseismic distance. This just shows what I already showed, so I want you to pay attention to the difference between these and this. So when you have station-specific training, it goes from that to that. Now we're getting down to about 0.38 error, and the more data we add, I think the better it's going to get. So just in summary, the global 3D models can significantly improve the accuracy of travel times. Computation time using a 3D model is a little bit too much for operational systems, but machine learning can be used to emulate this type of calculation and others as well. And our tests right now show that we're getting down to error from the 3D model itself. So in other words, the 3D model has a fundamental error. We're just below what that fundamental error of the 3D model is, and we'd like to push that even lower. And the most important thing is, once this thing is trained, right now we're getting travel times on the order of 10 microseconds on a single processor, like your laptop, operationally fast enough. And I'll stop there.
Well, thank you very much. Are there any questions? We have time for a question or two. There's one back there.
Yeah, maybe it's a stupid question, but what's exactly the difference between your approach and just brutally pre-computing all of the travel times and select the one you need?
Compactness. So the question was, what would happen if you just pre-computed everything and then just select it? And that was essentially, that would amount to having a 3D lookup for every station you could ever possibly imagine wanting to use. And So imagine you get this thing, you're not going to use it on your laptop. It's pretty big. And let's say the model changes a little bit. Now you got to recompute everything. So it really is compactness. You're taking all of this information and you are just densifying it into something that is hundreds of, maybe just kilobytes, and can be used to calculate really fast. And that's the operational implementation aspect.
Thank you. Any others? All right, we'll move on to topic 10, evaluation of event location performance compared to Cell 3 and NAICPD.
Good afternoon. I'm going to talk about a different topic at the IDC operations, the NetWizard algorithm, which is a kind of machine learning algorithm that's being tested for a number of years now. And here I summarize the latest results. We have my co-authors, Arnima Arora, who wrote actually the NetWizard software, and Ronan Lebras. So the motivation for this work is to evaluate the performance of the NetWizard. There are several caveats. The LEB is produced from the SCR3, so it is obviously biased toward the SCR3. So we need an independent bulletin which reflects the seismicity of the Earth, and we use, instead of the LEB, the USGS preliminary determination of earthquakes. There are no reviewed ISC bulletin yet, so our second best guess is the NAICPD. However, the NAICPD has a globally higher magnitude threshold. In other words, it produces fewer events globally than the LEB. And the NAIC also uses IMS data, so there is some correlation between the two. The data I'm using is one of the latest version of the NetWizard. Evaluating NetWizard is a kind of moving target, because by the time you finish something, they are already moved on to the second latest version. So this is just 3 months worth of data. And the VCEL 3, which is a separate pipeline running the NetWizard, is available through the external database. This version of the NetWizard and also the LEB does not use the SSSCs produced from the RSTT 3D global model. So, but we can relocate the LEB and the SCR3 with the iLoc, which uses RSTT to simulate the results, what would be getting if the RSTT SSCs were on. So just to summarize the results. NetWizard associates more phases on the left-hand side. You see the number of defining phases in the SCR3, which is the current automatic final bulletin, and the NetWizard. NetWizard uses much more phases, associates more phases than SCR3. These are on logarithmic scale, and this is the LEB. So the NetWizard produces a similar picture as the LEB, what the analysts are producing. And the bottom figure is the NAIC, which uses all stations available in the world. So also, one of our other important points, as I will show you some later, SCR3, the current method, tends to produce a lot of deep events, so push shallow events deep, which for monitoring purposes, that's the worst thing you can commit. NetWizard does not make this mistake. And finally, the LEB, if you compare the two figures on the bottom right-hand side, the LEB produces a similar depth distribution as the PDE. Just to show some pictures of the seismicity, the order is always the same. On the upper right-hand side is the SCR3. This is the NetWizard result. This is just a comparison, the PDE and the LEB. So this is the picture of the seismicity, what we are expecting. And as I mentioned, the PDE has a higher magnitude threshold, so most of the cases you have fewer events than the LEB. The point here is that SCR produces a lot more deep events, which may be either for false alarms or shallow events put into great depths, and for monitoring purposes, you don't want to put an event which is shallow to large depths. And the analyst will have to correct this thing, and if you see it in the LAB picture for the Peru-Bolivia-Chile border region, the analyst will have to manually remove these deep events. Another example, the Alaska and Aleutian and Kuriles Islands. Again, NetVisa produces a tighter seismicity picture. The events are better clustered. However, in this case, the PD is more complete than the LEB because it belongs to the US. And you see that the picture of the seismicity is quite similar what the analyst is finally producing. And also the NetVisa produces a very similar picture. We are losing this deep thing from SCR3. The same story here in the Japan-Kamchatka region. There are lots of deep events in SCR3, much fewer in the NetVisa, and the final seismicity is very similar as a result of the analyst work. In the Caribbean, the Caribbean is an interesting thing because the NESA-PD has a subducting slab here, which is completely missed by the IDSA, and all the IDSA pipelines missing this seismicity in the Caribbean. On the other hand, in the Mediterranean, this is the other way around. SCR3 produces, again, some strange seismicity, which is simply not there, and NetVisa goes overdrive. So it produces too many events. And I looked at the reported bulletins to the ISC. These are quite recent events, so it's only the IDC reports event. There are single array locations from NORSAR and Thessaloniki, which is the local regional agency. And probably these many events are driven by the single array locations from the NORSAR array, which can be 3.5 or magnitude 4-ish events, which the Greek network doesn't simply see. So these are probably false events. This is just a summary, my usual Venn diagram. On the bottom is the LEB, this is the NetVisa events and SCR3, and these are the number of events which are not in the LEB. And this is a kind of misleading number because NetVisa builds a lot more events, but at the same time, they may be, they could be valid events as well. So if you just look at the SCR3 events only, this is just a pepper and salt picture, and the NetVisa events which didn't make into the LEB actually show something similar to a real seismicity of the Earth. So these events could be very well varied. In the past, all the NetVisa studies were focusing on the seismic stuff, and now I'm looking at the three technologies separately. So for the seismic, this figure just shows the common events between the NetVisa bulletin and the lab. So these are the events which are common in the two bulletins. And again, this is on the right-hand side, lower right-hand side, those events which are not in the LEB. Again, I remind you that the LEB is produced for the SCR3, so most of the analysts wouldn't even have a chance to look at these events because the LEB was produced from a different bulletin. And, but many of these events could be actually real. So we would be seeing a completely different bulletin if the LEB would be produced from the NetVisa results. For infrasound, that's an interesting case. NetVisa builds quite a large number of infrasound-only events, mostly from two or three stations. Many of them appear to be fake, so this is just infrasound events are all over the world. They don't show any pattern. And And NetVisa, although it associates infrasound peaks to seismic events, did not build a single seismoacoustic event, which is strange because we do have large mines with large explosions, quarry blasts, so you would expect to see events with both infrasound and seismic phases being defining. And this could be just a procedural issue. When joining the seismic phases, NetVisa may apply with some different rules. I'm not entirely sure what's going on. And the analysts are building both seismoacoustic and infrasound-only events, which are here. So these are the seismoacoustic events with the known big, large mines in Central Asia and Northern America, and these are the infrasound-only events. The hydroacoustic bulletin is also an interesting case. NetVisa builds a number of hydro-only phases, so these are events NetVisa builds from H phases, and these are actually earthquakes. So that NetVisa also builds the same events from seismic phases, so you have two events, one built from hydroacoustic phases, and the other built from seismic phases only. And the analysts take care of this. They join the two events, they rename the H phases to T phases, and they throw them away. So again, I'm not entirely sure what's going on. NetVisa probably is allowed to rename a T phase to an H phase, so it will build an event, but then the analysts will rename it back to T phase and throw them away because the T phases are not used in the locations. So again, this could be some procedural issue which needed to be sorted out. To me, the interesting fact was that even if these are T phases, the azimuth and the time information is quite right. So these are information the analysts are throwing out. Now, as I mentioned, neither the LEB nor the NetVisa uses the SSSCs computed from a global 3D model, but use the current SSSCs, which only exist for a subset of IMS stations in the Northern Hemisphere. So what I was doing, I relocated the entire seismicity with ILOC, which uses RSTT predictions directly. And these are just the images, and this can be used to get a feeling what improvements the global 3D model travel time predictions can bring. So I quickly go through again. So ILOC now with RSTT uses even more phases than NetVisa at the first place. It's because more regional phases are associated using the better travel time predictions than before. And there are some differences between the origin time and the depth distribution, but those are explained by the different strategies of fixing the depth. The IDC procedure always fixes the depth to 0. ILOC takes the most probable depths. And these are the distance on the lower right-hand side. This is the distance distribution between the ILOC locations and the LEB. They are very similar, but it's a long-tail distribution. So there are at the tails there are large differences, and those are probably because of the regional phases. So better travel time predictions will give you improvements. Quickly going through again, these are the same pictures. What you can expect on the upper side, it is the LEB, and on the lower side is the NetVisa, so the original NetVisa, the relocated NetVisa, and just as a reference, the PDE, the NAIC PDE. And in general, it can be said that the SSSs, the RSTT predictions, improve the seismicity of the Earth, and I'm going to the conclusions. So the NetVisa provides improvements over the SCR3, the current pipeline automatic bulletin. It doesn't put shallow events to large depths, associates more phases in the location, and even those events which are not found in the LEB could be real. However, we have some remaining issues to be resolved with infrasound and hydroacoustic data. and applying the travel times from a global 3D model brings further improvements. Significantly more regional phases are used by this, and it provides both improvements in depth and location. And we would see a completely different LEB if we were using NetVisor together with the RSTT predictions. Thank you very much.
All right, thank you very much. All right, we should have time for one question if there's any questions that are out there. If not, we can move on. Move on to the recent improvements in the broadband seismic network of Iran.
Okay, good afternoon. I'm Said Soltani, a PhD student at International Institute of Earthquakes Engineering and Seismology from Iran. My presentation actually is about the recent improvements on broadband seismic networks of Iran. We're talking about implementation of tuned size COM3 and automatic online moment tensor inversion. My topics actually start with a question, and that's why we need a seismological network for Iran. Then we have a quick review on Iranian national seismic networks. Hereafter we call it INSN. And then we have a review of implementing tuned size COM3 in INS and automatic online moment tensor inversion program. And finally, we have conclusions. As you can see in the left map, Iran actually is located between two active tectonic plates. On the southwest, we have Arabia plate, and on the northeast, we have Eurasia. So these actually convergence forces makes that Iran is like a sandwiches, accommodated actually these forces. And there are many crustal deformations, which is in some cases, in some areas, caused destructive earthquakes in the past. Here, actually, we have the total seismicity of Iran since 19th century until recently, more than 160,000 earthquakes with magnitude greater than 2.5, which is actually a huge number. From this huge number, actually, we have some interesting numbers that you can see on the histogram, which is actually more than 1,700 earthquakes between 5 and 6, and more than 160 between 6 and 7, and more than 20 earthquakes bigger than 7. In this map, I just filter out the earthquakes with magnitude less than 5, and you can see that still there are a lot of earthquakes with magnitude greater than 5 since 19th century, and most of them are located in the borders in the southern, western, and northern part, which is actually pretty close to the main cities, so they are very dangerous. And on the left also you can just see some pictures about devastating earthquakes in Iran. On the bottom you can just see the BAM earthquakes in 2003 with more than 30,000 people dead. In the middle, we had actually Kermanshah earthquakes 2 years ago with magnitude 7.4, and also we had Balade earthquakes in 2003 with lots of injuries and casualties. So that was some good reasons that why we need a seismological network for Iran, for focusing actually and finding some areas with high potential. And that's actually the reason that's why we need a seismological networks. Nowadays, Iran, we have two networks with two goals. On the right, you can just see our international seismological network, which is actually called IRSC, which is responsible for announcing earthquakes. As you can see, they are actually, most of the stations are located near the cities because actually they wanted to actually report any local earthquakes. At the same time, actually we need some high-quality networks for advanced seismological studies, something 3D tomography, seismic noise, and so on. So we decided to establish another networks, which is all of the stations are broadband. We call it INSN, that you can see on the left pictures. Nowadays, we are actually in phase A. They defined actually 3 phases to improve the quality data and also number of stations. We are in phase A now with more than 29 stations, and after actually one of the important things that we have actually to be careful about them is the quality data that we are recording. For example, here there are 2 stations designed that we decided that to change the buildings from dome to vaults. As you can see from the PST on the left, which is actually related to the dome, then the minimum noise level is especially for high frequency, is very high, which is mostly related to the changing of temperature inside the stations. But when we use the vaults, which is actually a new design of our stations, you can see especially in high frequencies, it's reduced the noise level, and which is actually correlated very well with the minimum level of the global curve. So another steps that we are doing actually is monitoring our stations monthly with providing PSTs, as you can see on the left, which is one of the best, our best stations, which is located in the central part of Iran, which is Basiran, and also on the right, there is another station which is located in North Erpan, less than 50 kilometers north of Tehran, the capital. For both of them, you can see in a very broad frequency ranges that the noise level are very, very low. And our networks actually are provided some information with actually 2 categories. If you, for example, interested to have a bulletin of earthquakes, you can just go to this website and just click for each earthquakes, and then you have lots of information about that earthquakes. And if you also like to have a catalog, you can just go to this address again and just fill the blanks. Fill the forms, and you will have the data with the plain text, Nordics, which is a size and actually format, and GS2. About 6 actually months ago, we actually started a new project, rapid assessment of Iran seismic events. The reason of that, actually, this project was that after each big earthquakes in Iran, there are a lot of people that want to know what happens. And suddenly they actually go to our website, and after, for example, 2 or 3 minutes, 5 minutes, our website's being down. So we decided to actually design a new, actually a very light version website, and which actually for after each earthquakes, you can go to this website and have a lot of information about that earthquakes. Also, there is a automated generated reports with including actually lots of information such as focal mechanism, if possible, the last seismicity, shake maps, and also some other information that we are actually underdeveloped. So since 1960, we decided to use SeisCon3 because of the lots of stations are available nowadays. For example, thanks to IRSC and GFZ, we have lots of stations around Iran, such as Afghanistan, Iraq, KSI, and others. And also, we had a cooperation with Iran Seismological Network, so we decided to use SeisCon3 to actually to put together all this information. And we did some actually tuning on SeisCon3, which actually was defining a new grid and doing some actually playbacks with defining some new configurations, which is actually peaking filters. And also we used an optimized velocity model for Iran, which we derived using our information. And then actually For each earthquakes, nowadays we can process actually for each earthquakes less than 2 minutes, which is quite good. Sending emails and SMS actually are another project of our networks. After each earthquakes, there is actually automated GMT maps that includes all past events, the historic seismicity and focal mechanism gathered automatically from global CMT, and then provide a map and send to the decision makers. That might be very helpful for them. Another thing that which is very important for us is actually taking care of the SeisCom performance. So here we have some comparison in terms of longitude and latitude and magnitude with another actually Iranian actually seismological networks. As you can see, for longitudes and magnitudes, the automated SeisCom events actually with the operation results are very well, and for the magnitude, we are still doing some task that which is not bad, but I think we can do better. Also, we had operated automatic online moment sensor solutions that we actually used the Draeger code. So after each earthquake with magnitude greater than 4, we actually had something like this flowchart. We have waveform quality check first based on time series gap and signal to noise ratio and some other things. And then we have waveform selections based on azimuthal gap. And then we have some pre-processing, for example, filtering the waveforms, making green functions, and so on. And then we run a Python code, which is actually implemented Draeger code for doing inversion. And then we have a quality check, and if the answer is yes, it will save to the actually our archive. And then if the answer is no, just repeat the process. So another steps that actually we have to do is to be careful about the automatic moment sensor solutions. In these pictures also you can just see the comparison that we have done between our results and the global CMT. As you can see here also on the on the right, there are 2 minutes. Okay, it's the last one. As you can see here, also there is a very good consistency between them, and also from the focal mechanism, also you can just see that they are very consistent with the seismotectonic of the region. It's noteworthy that I have to say that there are lots of ISI papers, master thesis, and PhD thesis are doing with our database, and on the right also you can just see lots of aftershock studies that have been done using our networks. And for the conclusions, these are, I have to say that the total number of affected seismic stations in ISN is reached 29. We hope that the phase B will be reached in 2025. RAISE is a very light version of our website for getting information more quickly and informative than before, using SeisCom 3 all earthquakes with magnitude greater than 4.5 are processing automatically using 29 INS stations, and extra 35 stations belong to other networks. This yields reduction in uncertainty for earthquake location parameters. Automatic online moment sensor inversion are developing and helps to better understanding of major earthquake source parameters. Thank you for your attention.
Thank you. We have time for a few questions, if there are any. If not, we can move on to our last topic of the day, machine learning tool NetVisa from cradle to adulthood.
Good afternoon, and thank you for staying so late in this warm day today in Vienna. I'm going to talk about NetVisa. You heard the name a lot already, especially this afternoon with Istvan's presentation, who was assessing it against other bulletins. So this talk is basically about how we went from a research prototype to an operational system. And it took about 10 years or so to achieve this. And this is the outline of my talk. So I'll start with some background and the history of R&D and putting NetVisa into operation, some of the accomplishments that we went through by placing NetVisa into operations, and the plans for the future. So from an initial presentation at SnT, and the first one was at SnT 2011, we went to a practical proof of concept, and then at a session of the technology refreshment, which is one of our PMO policy-making organs meetings, a proposal was made to continue the work and develop a working prototype. Then some offline testing was done, the results of which was provided to experts for evaluation. And then this led to testbed testing, and then finally to operations. So between the time that the first presentation was made at SnT, which was 8 years ago, and last year, which is when it finally became operational, this is about a span of 7 years or so. So to place the NetVisa software in the context of the processing chain, I'm showing here the flow of data. So primary seismic, hydroacoustic, auxiliary seismic, and infrasound, going first into station processing, and then later on into network processing, producing the cell 1, cell 2, and cell 3, which are automatic bulletins produced for the cell 1 at 1 hour after real time, cell 2 is 4 hours after real time, and cell 3 6 hours after real time. Cell 3 is reviewed by analysts to produce the reviewed event bulletin, which is one of the main products of the IDC. So GA, Global Association, is the current the software that currently produces cell 1, cell 2, and cell 3. And both NetVisa and GA, so NetVisa is the new generation, but they both take parametric data, detection data, after station processing, and they produce bulletin data, so events, basically, lists of events automatically. There were discussions even back in the early days of applying machine learning to the problem of automatic association, which is what we call going from detections to producing bulletins of SIGVISA. And if maybe some of you were attending the panel on artificial intelligence in the FESSAL, where Professor Russell explained some of the features of SIGVISA. SIGVISA essentially is a more ambitious step that would involve going directly from waveforms to producing bulletins. But NetVisa goes from parametric data to producing bulletins. So I'm not going to spend too much time on explaining the algorithm. I would refer you to the paper by Aurora et al., BSSA 2013. But essentially, what NetVisa does is it considers a hypothetical world where events are denoted as E on the graph to the left of the slide. Arrivals associated with events are denoted as by lambda. Detections not associated are denoted by xi, and coda arrivals are denoted by kappa. So the arrows indicate dependence between these elements, and the job of NetVisa is to figure out the structure of this graph by finding the events and the arrows that connect events to detections within a time interval t. So taking all the detections that are given to it, it will try and find the best fitting graph given a probabilistic model. That probabilistic model can be refined as more is learned from the reviewed bulletin. So again, not going into too much detail, there are elements of the probability model that are shown on this slide. One of them is the seismicity prior. So basically, we have an idea of where most of the earthquakes occur on the surface of the globe, and we're using that as an input. And it should be noted at this point, since we're looking at detecting events that are not earthquakes, that are explosions, not necessarily in areas that are seismic, we have to add some uniform probability distribution to this, and we do that in the current system. The figure at the bottom shows a prior that is used for travel time residual, and this is the case of the P phase at station Alice Springs in Australia. And these distributions, so the probability model is learned from the reviewed bulletin itself. And we are using a Laplacian model for the P phases as well as for the P phase residual as well as for the azimuth residual. So very shortly. So these are the steps that were taken during the initial research and the various research works that were presented concerning NetVisa in the last 10 years or so. So there was an initial workshop in 2009 that we called the Boot Camp for Seismology, where seismologists and machine learning experts, data mining experts, came together in Vienna and spent a week basically exchanging and trying to figure out what we could use in as a machine learning tool to apply to the CTBT problem. And one of the ideas that came out of that, there was a young graduate student, Nima Arora at the time, who got very enthusiastic about the automatic association problem, and that's basically where where NetVisa came out. There was another meeting in 2009, in June, where there was a presentation poster in a data mining session. Then a technical meeting, a larger technical meeting in November 2009 about multi-sensor data fusion with a bit more progress. Finally, the presentation by Professor Stuart Russell at the technology refreshment session of Working Group B. A workshop in Montpellier at the ESC, jointly with the ESC in 2010. And finally, the SnT 2011. And after that, a paper was published, 2013, so that's kind of the fundamental paper on this Bayesian method as applied to the automatic association problem. And various work were presented at the SnT meetings. In terms of the history of developments and finally the putting NetVisa into operations, in terms of feature additions and improvement, between 2012 and 2013 were the early development and tests for the seismic part of the system. Between 14 and 15, we had the addition of hydroacoustic, and Mark Pryor, who was the former hydroacoustic officer, was very active with this. Between 2015 and 2017, the addition of infrasound, Pierrick Mial was very actively involved with this as well. And then between 2016 and 17, we had the development of the analyst interface. The idea was to allow the analysts to access the results of NetVisa, which were proven to be quite interesting for them, without disturbing the current operational system. So to have, in addition to the cell 3, to have what we call the vCell 3, which Istvan mentioned in his talk, and which basically presents to the analyst the events that the cell 3 had not found. And then between 17 and 19, improvement for regional velocity models and events, which are actually not yet incorporated into operation. So in terms of testing and operational implementation, between 2013 and 14, the initial testing by analysts was done with positive results. Between 2015 and 2017, offline testing on 1 year of data with a 3-pipeline operational configuration, but completely offline was performed. And then in July 2017, the VCell3 finally started operationally. The results were examined by analysts, but not used yet in the REB bulletin. And it's only starting in January 2018 that they actually started using the VCell3, but only with the primary seismic data. And from June 2018, and that's the current status, the analysts use systematically the VCell3 complete SHI. In terms of the results and what did NetVisa accomplish to help with the automatic association problem. This is 1 year of data, 2013, that has been tested intensively, and this is a cell3 for that year. If we look at the LEB, which is the reviewed bulletin, it is a more complete bulletin than the REB. The LEB contains everything. The REB contains only the larger events that have to pass a certain threshold. And this is the NetVisa. So if you compare LEB and NetVisa, it's pretty clear that, they have much more in common than if you compare cell3 and the LEB. So clearly, there's something there that NetVisa is doing correctly. More quantitatively now, comparing the overlap for that same year and using version 2248 of NetVisa. What you see here is in blue the overlap between the REB and NetVisa. The overlap means how many events, what percentage of events are common to the REB and the reviewed bulletin. In green, you have GA, so we are about 10% lower with a GA. GA is Global Association. Again, that's the standard software that we are using at the IDIC. It's clearly much better to have a larger overlap with the reviewed bulletin. That means that the analysts would have to work less if they reviewed the NetVisa bulletin. In purple, you have the inconsistency for NetVisa and for GA. So in that case, they're fairly similar, let's say, but with a little bit of a little bit worse for NetVisa, actually. Another comparison that we did was using ground truth events that are completely independent of the REB and of the CTBTO results. So the ground truth events for 2013 from the ISC, from the ISC website, so you can get them. They are published by the ISC. And what we see here is that out of a total of, I think it's roughly, a total of 292 events. It's on the first line there, total ground truth events. You can see that the performance of NetVisa in terms of getting those events is much larger than the cell3. We have a lot more ground truth events that are found. It's even better than the LEB, right? So 126 in the LEB, 135 in NetVisa, and 99 only in the cell3. Out of the ground truth event, 144 are too small to even be in any of them, in any of those automatic bulletins or reviewed bulletin. So that's a very compelling test because it's a completely bind test essentially. Now that we are in operations since January 1st, and it should say 2018, we have been able to compare in operations the results of NetVisa. And what did we gain? So what you see here in blue is and this is a logarithmic scale, and this is by intervals of MB. In red, you see the NetVisa events, the events that we know have a provenance in NetVisa. In yellow are the events that come from a process that the analysts use, which is called scanner. That's an interactive process that pulls in very small event that has a very high rate of false alarms. And the green ones are the ones that are obtained by the analyst only, so they were not in any automatic bulletin. And in a nutshell, what we confirm is the 10%. You remember the graph was 10% overlap 10% better than GA. This is confirmed, and mostly the smaller events, so events smaller than magnitude 4, are obtained by VCell3, by NetVisa. Now, when we look at the even smaller events that only have a local magnitude, we see that the results are similar, and I would say actually much better for NetVisa. So we have a confirmation that we are doing a good job in terms of missing fewer events with NetVisa operationally, and contributing to the REB in a considerable way, in about 10% or so. I'm coming to the conclusion. So the next step will be full replacement of global association. The analysts will review VCell3, which is going to be the result of a 3-pipeline processing, and an upgrade to the newer version of NetVisa, which is compatible with the NDC in a box version. I should have mentioned that one of the latest development is that we will be providing NDC in a box, providing NetVisa with NDC in a box as a SizeComp module. And that version also contains improvements for regional events and aftershock processing. And then the other work that we do around NetVisa is to set up synthetic test cases for stress testing of NetVisa. So NetVisa can also be used as a forward model to insert specified explosion with specified magnitude into a background of a natural background, essentially. And this concludes my talk. Thank you.
Thank you. We have time for a quick question or two, if there are any. Oh, there's two.
Yes, lots of histograms. So I understand then that the analysts have been looking at systematically at the NetVisa only events for nearly a year now, and so my question is, what has been the result of that? I mean, are the analysts, are we able to say, or are they investigating why these events are cell3 only, or are NetVisa only, or are they simply reviewing them and then putting them into the LEB if they are meet the event definition criteria? That's
okay. So the way it works, well, first of all, they are not reviewing the VCell3 per se. The VCell3 is produced in parallel to the cell3, so it's there in the background. What they are doing is using a tool, an interactive tool that pulls, once they are done with the cell3 review, it pulls up the events that were only seen by the VCell3. They're not reviewing the complete VCell3 bulletin yet. That will be a next step. So, and the provenance, so how are we able to tell from an REB event, for an REB event, where this event came from? And that's through the EVID. Basically, that's a very simple way to trace which event was reviewed. So in blue, what you see in blue on this histogram, and this is, again, this is a logarithmic scale, so the blue bar would be much bigger, of course, in a linear scale, and the height of the red bar is about 10% of the blue bar. So roughly, it's not exactly 10% in all of these MB intervals, but we can trace. So we thought ahead basically in terms of design, and we thought that it would be good to be able to tell what kind of improvement we get. So we trace the IVID also of VCell3 events, and that's how we can tell.
Thank you. Our last session question will be here on the right if it still exists.
Thank you, Ronan. Just one question. As you mentioned, Professor Russell also presented the SIG visa. Right. Do you have any plan to implement the SIG visa in future of IDC? I mean, starting, evaluating?
Well, I think a good forum for evaluating SIG visa initially would be to to do it as a prototype. We do not have immediate plans. We just finished putting into operation something that took 10 years to go from a research concept to a prototype to something that's operational now. So, you know, let's give it maybe another 10 years for NetVisa to work and produce and improve on the REB, and maybe test visa SIG visa in parallel in a realistic context offline, and see what we get. I imagine that maybe Professor Russell was at the origin of both NetVisa and SIG visa. Nima Arora was his student. I would imagine, he didn't mention the computing power that we need to run SIG visa, but I would imagine it's quite considerable. So maybe on the regional scale, it's possible, and on the global scale might be a lot more complex to apply right now. But thanks for the question. That's a very good question.
Okay, thank you. Now, subject to any comments by my colleagues here at the table or from the audience, I think we're ready to wrap up this session. Thank you for enduring the marathon of the afternoon. Have a good night.
It's a long session.